Tonight, we're going to examine something that seems really simple, but in reality it's just one of the most mind-bending ideas in all of science. It's called a light year. You've all heard that word thousands and thousands of times before. Scientists toss that word around all the time in their discussion of space. But when you really understand what a light year is, when you understand how big a light year is, it changes the way that you view the universe. It's more than just a large number. It's a scale so big that it pushes the limits of how we can understand it. And at the end of this journey, you'll see why scientists require this unit, and why it's the only one they could use. Let's start with something you can understand: distance. You understand distance in your everyday life. You know how far it is from the grocery store, from your office, from the next town over. These distances you can easily relate to because you've driven or travelled them. You have some idea of what these distances entail in terms of time, in terms of the toll, in terms of what you will see along the way. A kilometre is the distance you can walk in 10 to 12 minutes at an average pace. These units of distance will serve you perfectly in your everyday life. When someone says you have to drive 5 kilometres to get to the store, you have some idea of what time you can expect it takes. You can almost picture the drive in your head. Maybe you pass a couple of traffic lights. Maybe you get a look at some familiar sights. This distance you can relate because it's concrete. When someone says how the next town over is 200 kilometres away, you can easily plan your trip. This will take you 2 hours of driving time. Fill up your gas tank and maybe grab some sandwiches. The plan will then include a rest stop halfway. The scale of these distances is human. They live in our reality, our understanding. We have learned through our own evolution the size distances that make up our day, our horizon, our distances that define our survival, our distances that define our routes. But all these measurements start becoming clumsy when large distances come into play. Before we dive into this cosmic puzzle, let's take a moment to appreciate the scale of it all. This story is travelling across the globe, reaching you right now. I'm always curious to see our small planet mapped out in the comments, so let me know which part of the world you're joining this exploration from. And if you believe these cosmic stories are worth exploring, the best way to support our mission is by liking this video and subscribing for the next one. The distance between New York and Los Angeles is 4,500 kilometers. That's not so large a number. It's a 5-hour flight. That's how often people make this trip. They cross this country. They witness the diverse topography changing all the way, the East Coast cities veering off into the plains of the Midwest, then the rock faces of mountains, then after that the desert stretches of the Southwest, until finally the Pacific coastline comes in sight. The trip is long, but it can be done. It is humanly possible. The circumference of the Earth around the equator is 475 kilometers. That, of course, is a large number. Early explorers sailed around the world, so we know it's possible to travel that distance, even if it takes months. Ferdinand Melon's expedition took 3 years to circum the globe from 1519 to 1522. Modern commercial flights can circle the Earth in about 45 hours, if you could book connecting flights that went all the way around. The Earth is large from our perspective standing on its surface, but it's not incomprehensibly large. It's a finite thing you could in theory explore completely. But now let's go bigger. The distance from Earth to the Moon is approximately 3084,000 kilometers. This is where normal measurements begin to feel insufficient. 384,000 kilometers. It's hard to picture in any meaningful way. It is not across the country and back again. It's not around the world in a sailboat. It's something entirely different. There is no road to follow, no landmarks to pass, no roadside rest stops along the way. It's just distance, pure distance across open space. How would you even begin to travel that far? The Apollo astronauts took about 3 days to travel from Earth to the Moon, using powerful rockets that accelerated them to speeds of about 11 kilometers per second. That's about 39,600 kilometers per hour, roughly 400 times faster than highway driving. Think about that for a moment. 400 times faster than you've ever driven. And even at that incredible speed, which required some of the most powerful rockets ever built, burning enormous amounts of fuel, it still took 3 days. 3 days of travel through the vacuum of space at velocities that no man had ever been subjected to before in order to reach our closest celestial neighbour. And this is simply to the Moon, the closest celestial body to planet Earth. The Moon is close enough that it can be viewed with the naked eye. Enough detail can be observed from the surface of the Moon using no more than a pair of binoculars. It's right there in the sky. Yet it takes 3 days of space travel to reach it. Once we begin discussing the distances to other planets, the Sun, other stars in space, the kilometre measurement becomes completely irrelevant. The numbers become so big they distort all meaning. They are reduced to abstractions that exist on paper, as opposed to distances that you could understand. Of course, the distance from Earth to the Sun is 150 million kilometres. Try to put your mind around that. You can't, can you? Your mind just kind of registers it as an old big number, but you certainly don't understand what that number represents. Nothing in your life prepares you for a distance like that. Nothing in human evolutionary history prepared us to think in terms of distances like this. We were designed to think in terms of distances to water, to hunting grounds, to how far we could walk. We couldn't have possibly developed an understanding of something like 150 million kilometres. The Apollo missions that carried human travellers to the moon had an average speed of 11 kilometres per second. It would take this much time, around 160 days or 5 months, to reach the orbit of the Sun. The fastest moving man-made object, although not the most advanced, is the Parker Solar Probe, which has a speed of up to 192 kilometers per second when it is closest to the Sun, using the gravity of the Sun to accelerate itself to achieve ever higher speeds. Even with this phenomenal speed, which is 17 times that of the previous record holder, the Parker Solar Probe takes several months to orbit the Sun, and this star is close to us. It is in fact in our neighbourhood in space. It is the star we orbit. It is what gives off all of the light and all of the warmth necessary to keep life alive on Earth. We watch it every day, in fact. We see it in the sky. It is so familiar to us. However, this star is also 150 million kilometers away from us. That is so large in comparison to what we have in this galaxy. In fact, it takes our most advanced spacecraft many months to reach it, even at today's current speeds. Once we get to talking about other stars in relation to distances, we will see why this is so in comparison to what we will be learning soon. The Sun is, of course, our closest star, and it is also 150 million kilometers away from us. The next closest star to us is named Proxima Centauri. It is in fact 26 to 6,000 times farther away than our Sun is to us. 26 to 6,000 times longer than the longest distance that our fastest moving spacecraft has yet been able to reach. It's why astronomers required a new way to measure distances, not because they enjoy complicating things for the rest of us, not because they want to confuse us with big numbers, but the fact is that kilometers are simply too small for measuring the distances between stars. Measuring the distances between stars in kilometers is like measuring the distances between nations in millimeters. It's possible, but ineffective. Light is one of the most fundamental aspects of our universe, yet it also remains one of the most mysterious and fascinating phenomena. At its core, light is a form of electromagnetic radiation, a wave of energy that travels through the vacuum of space at an astonishing speed, approximately 300,000 kilometers per second. It is the reason we are able to see, the force that powers photosynthesis in plants, and the medium through which we observe the distant cosmos. In physics, light is characterized both as a wave and as particles, an idea that might seem contradictory at first, but is key to understanding its true nature. This duality is a cornerstone of quantum mechanics, where light can behave like a wave, spreading out and interfering with itself, and yet also act as a stream of particles known as photons. Photons are massless particles that carry packets of energy, and their behavior can be described by quantum electrodynamics, a branch of physics that explores electromagnetic interactions at the smallest scales. The wavelength of light is a crucial property. It determines the kind of light we see or detect. For visible light, wavelengths range roughly from about 400 nanometers, violet, to about 700 nanometers, red. Shorter wavelengths lead to higher energy photons, which is why ultraviolet light and X-rays are more energetic and can cause damage to biological tissues, while longer wavelengths, like infrared and radio waves, carry less energy. The frequency, which is the number of wave cycles that pass a point every second, is inversely related to wavelength. As wavelength gets shorter, frequency increases. Another key characteristic is amplitude, which influences the brightness or intensity of the light. A wave with a larger amplitude carries more energy, making it appear brighter to our eyes. The polarization of a light describes the orientation of its electric field oscillations, and this property is exploited in sunglasses, photography, and various scientific instruments to analyze or control light. In a broader sense, physicists also describe light using its energy and momentum, which are conserved quantities in physical interactions. The energy of a photon is directly proportional to its frequency, determined by Planck's constant, a fundamental constant of nature. This relationship is encapsulated in the simple equation: energy equals Planck's constant multiplied by the frequency. Furthermore, light interacts with matter in complex ways, absorbing, reflecting, refracting, and scattering. Each interaction revealing more about the properties of the material it encounters. It is through these interactions that telescopes detect distant stars, microscopes reveal tiny biological structures, and lasers enable myriad technological advances. So, light isn't just something that fills our world with brightness and colour. It is a fundamental piece of the universe's puzzle. Its wave-particle duality, interconnected properties of wavelength, frequency, and energy, and its ability to propagate across unimaginable distances make it one of the most astonishing marvels in physics. Understanding light isn't just about comprehending how we see, it's about unravelling the very fabric of the cosmos itself, an endless journey from the known to the unknown. Wave-particle duality is at the very heart of how we comprehend light, shattering our expectations and forcing us to think beyond simple categories. For centuries, humans saw light either as a wave, rippling through water or vibrating in a string, or as tiny particles zipping through space like grains of sand. But as science advanced, it became painfully clear that light refuses to be pigeonholed into just one of these descriptions. Instead, it embodies a bizarre hybrid of both, depending on how we observe and measure it. Imagine shining a beam of light through a slit, and instead of just two bright spots where the light hits the screen, you see a sprawling pattern of bright and dark fringes. This phenomenon, known as interference, is the signature of waves. Light seems to spread out, overlap, and interfere with itself, like ripples in a pond colliding and creating a complex tapestry of peaks and troughs. It's a beautiful display of wave behavior, showing how light can be spread across space, constructively and destructively interacting with itself. But then, turn around and look at the photoelectric effect, where shining light on a metal surface causes electrons to be emitted. This process baffles if you think of light as just a wave. Why? Because classical wave theory predicts that increasing the light's intensity should give electrons more energy, but experiments showed that there is a threshold frequency below which no electrons are ejected, regardless of how intense the light is. Instead, what happens is that light arrives in discrete packets of energy, photons, that jolt electrons out of atoms. Here, light behaves like a stream of tiny pulsating particles, each carrying a quantum of energy proportional to the light's frequency. This duality isn't just a curious oddity, it rewrote the foundation of physics. Max Planck's work on blackbody radiation hinted at quantization, but Albert Einstein's explanation of the photoelectric effect cemented the idea that light has both wave-like and particle-like properties. It's as if light is a chameleon, adopting the mode of description that fits the situation best. Measure its bending and interference patterns, and it acts like a wave. Measure its ability to eject electrons, and it acts like a particle. This wave-particle duality leads us to a universe that refuses to be simple. It shows us that the nature of reality isn't confined to classical ideas, but exists in a strange, delicate balance. Light behaves as if it's spread out across space, giving us interference and diffraction, yet it delivers its energy in discrete chunks called photons. These photons obey the strange rules of quantum mechanics, probability waves that only arrive at a detector when measured, collapsing into particles. What does this mean for our understanding of the universe? It means every observation teeters on a knife edge, sometimes wave, sometimes particle, and everything we think we know is a shadow of deeper, more mysterious truths. The universe doesn't conform to our neat categories. It reveals that at its most fundamental level, light, and perhaps everything else, transcends simple labels. It demands a new language of description, one that embraces ambiguity and probability, where light's true nature is revealed not through clear-cut definitions, but through the act of measurement itself. Electromagnetic radiation is a fundamental aspect of our universe, serving as a cosmic messenger that travels across vast distances to bring us information about the cosmos. To understand what makes this radiation so unique, we need to explore its key properties. First, wavelength is perhaps the most recognizable property. Wavelength is the distance between two successive peaks or troughs in a wave. In the electromagnetic spectrum, wavelengths range from long radio waves, measuring meters or kilometers, to very short gamma rays, less than a trillionth of a meter. Wavelength determines the radiation type: radio, microwave, infrared, visible, ultraviolet, X-ray, or gamma ray, and influences how it interacts with matter. Closely related is frequency, the number of wave cycles passing a point each second measured in hertz. Wavelength and frequency are inversely related. Shorter wavelengths mean higher frequency, longer wavelengths mean lower frequency. This relationship affects the energy carried by the radiation. Higher frequency waves have more energy per photon. Photons are the particle-like units of electromagnetic radiation, each carrying a discrete packet of energy proportional to its frequency. Given by Planck's constant times the frequency, a gamma-ray photon is highly energetic, capable of destroying molecules and damaging DNA. Conversely, radio wave photons carry minimal energy, passing through buildings and the human body with little interaction. Photons' energy dictates how they interact with matter, whether they excite atoms, ionize molecules, or pass through objects. Polarization is another key property, the orientation of the electric field oscillations in the wave. Some waves are polarized in specific directions, revealing information about phenomena like the cosmic microwave background or scattering effects caused by Earth's atmosphere. Polarization helps scientists understand the environments of distant sources and the presence of magnetic fields in space. Intensity describes the power of radiation per unit area, indicating how bright or faint a source appears. Intensity decreases with distance, following the inverse square law. Power diminishes proportionally to the square of the distance from the source. This explains how distant stars can be visible across immense distances yet appear faint, illustrating the effect of space on the propagation of a light. Electromagnetic waves also exhibit velocity, traveling at the speed of light in a vacuum, approximately 300,000 kilometers per second. This universal speed limits how quickly information or matter can move across the universe. The constant velocity influences our measurement of cosmic distances and the timing of events in space. Understanding these properties reveals how light behaves and how we measure and interpret cosmic phenomena. When we say a galaxy is 10 billion light-years away, we refer to the time light takes to reach us, with its wavelength, frequency, energy, and other properties having travelled across the cosmos at the speed of light. This foundation helps us grasp the universe's staggering scale, which often challenges our perceptions of space and time. These properties, wavelength, frequency, energy, polarization, intensity, and velocity, are fundamental to studying electromagnetic radiation. They shape our understanding of how light propagates, interacts with matter, and allows us to observe the universe. Together they underpin our knowledge of the cosmos, from the smallest particles to the largest structures. Recognizing how these properties work enables scientists to decode the universe's message, understanding everything from the birth of stars to the evolution of galaxies. Measuring the speed of light has been a journey spanning centuries, filled with brilliant experiments and groundbreaking insights. It all started with early philosophers pondering whether light travelled at all, but it wasn't until the dawn of the 17th century that science took definitive steps toward measuring its velocity. One of the first notable efforts was by Danish astronomer Ole Rømer in 1676. He observed the eclipses of Jupiter's moon Io and noticed that the time between eclipses varied depending on Earth's position relative to Jupiter. When Earth was moving away from Jupiter, the eclipses seemed to be delayed. When moving closer, they occurred earlier. From these observations, Rømer deduced that light takes a finite amount of time to travel the distances involved, effectively providing the first estimate that light has a measurable speed. But capturing a precise value was a challenge for centuries. Fast forward to the 19th century, when scientist Armand Fizeau devised a method involving a rotating toothed wheel and a beam of light. His equipment consisted of a beam projected through a partially silvered mirror towards a rotating wheel with teeth. Light passing through gaps in the wheel would reflect back from a distant mirror. When the wheel spun at a certain speed, the returning light would be blocked by the teeth, effectively turning off the beam. By adjusting the wheel speed and measuring the point at which the beam was blocked, Fizeau could calculate how long it took for light to make the round trip over a known distance. From this, he was able to estimate the speed of light to be roughly 299 million meters per second, a value astonishingly close to the modern measurement. Following Fizeau, Léon Foucault refined the measurement with a rotating mirror experiment. Instead of a toothed wheel, Foucault used a rapidly spinning mirror that caused the reflected light beam to shift slightly, based on the mirror's rotation speed. By carefully measuring this shift over a known distance, he achieved a more precise value for the speed of light, confirming it at approximately 300 million meters per second. Why is measuring this speed so significant? Because it disrupted the very way humans understood the universe. Knowing that light travels at a finite speed shattered the centuries-old assumption that it was instantaneous. This realization opened the door to deeper questions about the structure of space and time. If light takes time to reach us from distant stars and galaxies, the cosmos we observe is actually an image of the past, a snapshot taken that instantly. When we look up at the sky, we're peering back through light years, glimpse after glimpse into the universe's history. Furthermore, establishing a consistent value for the speed of light became a cornerstone for Einstein's theory of special relativity. It was the universal speed limit. Nothing could travel faster than light, and this invariant velocity fundamentally changed the notions of space and time themselves. Without precise measurement, these revolutionary theories might have remained concepts rather than scientific truths. The significance of measuring the speed of light extends beyond theoretical physics. It underpins technologies we rely on daily. Satellite communications, GPS navigation, and optical fibers all depend on understanding how light travels through different mediums. As we push the boundaries of exploration, traveling to distant exoplanets or looking back at galaxies billions of light years away, this measurement remains our guide, reminding us of the vast, mind-bending distances that define our universe. Light, often seen as a simple wave or stream of particles, is actually a versatile traveller that interacts with matter in many ways. These interactions shape our universe, allowing us to see stars and understand distant galaxies, while also presenting profound mysteries at cosmic scales. One common interaction is absorption. When light meets matter, its energy can be taken up by atoms or molecules. For example, shining a flashlight on a black wall results in the wall absorbing the light energy, warming slightly. On an atomic level, this excites electrons, shifting them to higher energy states. This process is fundamental to how we detect light. Our eyes and instruments are designed to pick up absorbed photons. The colour of an object depends on which wavelengths it absorbs or reflects. Reflection occurs when light bounces off a surface. Think of a mirror. Light waves hit its smooth surface and bounce back at equal angles. Reflection isn't limited to shiny surfaces. It happens across various scales, from the sparkle of fish scales to frost on a window. The surface's roughness and material determine whether reflection is sleek, specular, or scattered in many directions, diffuse. Refraction, a more enchanting interaction, occurs when light passes from one medium into another and bends. This bending happens because light changes speed in different materials. For instance, when light moves from air into water, it slows and bends toward the normal line, creating effects like a bent straw in a glass or an object appearing displaced underwater. Refraction underpins lenses, microscopes, telescopes, and optical instruments that reveal the universe's secrets. Diffraction is another fascinating process, occurring when light encounters obstacles or openings comparable in size to its wavelength. Instead of passing straight through, light spreads out and produces intricate patterns, bright and dark fringes, such as the rings seen around a central bright spot through a small slit. Diffraction helps us understand light's wave nature and interference patterns in experiments that demonstrate wave behaviour. Scattering is prominent both on cosmic and everyday scales. When light hits tiny particles like molecules in Earth's atmosphere, it scatters in many directions. This explains why the sky appears blue. Rayleigh scattering favours shorter blue wavelengths over red. Similarly, interstellar dust scatters starlight, creating diffuse nebulae or making distant objects seem dimmer and redder, a process called interstellar reddening. Transmission, the passing of light through a medium, is crucial in many contexts. Transparent materials such as glass or water allow light to pass with minimal absorption or scattering. This enables everything from our windows to telescopes that peer into the depths of space. Transmission is fundamental to observation, letting us collect photons travelling across vast intergalactic distances. Each of these interactions, absorption, reflection, refraction, diffraction, scattering and transmission, are basic but profound processes that dictate how light explores matter at all scales. Studying them helps scientists decipher the universe's grand design, transforming faint light from billions of light years away into stories, images, and insights that reveal cosmic secrets. As we push the limits of observation, the continuous dance between light and matter challenges and inspires us, offering endless opportunities for discovery. Astronomers have developed an array of units to measure the vast expanses of space, each tailored to different scales and contexts. When we talk about distances within our own solar system, we typically use units like the astronomical unit, or AU. 1 AU is roughly the distance from Earth to the Sun, about 150 million kilometers. It's a handy measure for comparing planetary positions and understanding the scale of our solar neighborhood. But when we look beyond the planets and into the realm of stars and galaxies, the AU becomes too small to be practical. That's where the light year comes into play. A light year is the distance light travels in 1 year, which is approximately 9.4 trillion kilometers. It's a staggering number, but it helps us grasp how far away celestial objects are. For instance, Alpha Centauri, our closest star system neighbour, is about 4.3 light years away. That means the light we see today from Alpha Centauri left that star over 4 years ago, travelling across the galaxy at a mind-boggling speed of light. For even larger distances, especially between galaxies, astronomers often use the parsec. 1 parsec equals about 3.26 light years, or roughly 30.7 trillion kilometers. The name comes from parallax of 1 arcsecond, which refers to how the apparent position of a nearby star shifts relative to distant background stars when observed from different points in Earth's orbit. Parallax measurements are fundamental for calculating distances to stars nearby and have been crucial in anchoring our cosmic distance scale. Beyond these, we sometimes refer to the megaparsec, 1 million parsecs, which is useful when measuring the vast separations between entire galaxy clusters. At this scale, distances stretch into hundreds of millions of light years, and it's a testament to just how expansive the universe truly is. In recent times, astronomers have also employed redshift as a kind of cosmic ruler. As the universe expands, light from distant galaxies is stretched out, shifting toward the red end of the spectrum, hence redshift. By measuring how much the light has shifted, scientists can estimate how far away those galaxies are and how long their light has been travelling to reach us. This method becomes especially valuable when dealing with objects billions of light years away, where traditional parallax isn't feasible. All these units, astronomical units, light years, parsecs, megaparsecs, are like different lenses through which we view the universe. They allow us to translate the unfathomable distances into numbers we can grasp and calculations that help us understand the universe's size, its age, and our place within this vast cosmic tapestry. When you think about it, each one tells a story, not just of space, but of human curiosity and our relentless quest to explore what lies beyond the stars. To grasp how vast the universe is, astronomers need creative tools and methods. The distances involved are so immense that ordinary measurements are impossible. Instead, they rely on the properties of light travelling across space. One essential method is parallax. Imagine holding your finger in front of your face and switching between your left and right eye. Your finger appears to shift against a distant background. That's parallax. Astronomers do the same on a cosmic scale by observing nearby stars from different points in Earth's orbit, about 6 months apart. The apparent shift relative to background stars allows them to calculate the star's distance using basic trigonometry. Parallax works for stars within a few thousand light years, but beyond that, shifts become too small to measure accurately. For more distant objects, astronomers use standard candles. Objects with known intrinsic brightness. Knowing how bright a light source truly is allows astronomers to estimate its distance based on how dim it appears. Cepheid variables are pulsating stars that serve as excellent standard candles. Their brightness oscillates regularly. By measuring their pulsation period, astronomers determine their true luminosity. Comparing intrinsic luminosity with observed brightness reveals the star's distance, up to thousands of light years, beyond Cepheids, supernovae. Especially, type Ia supernovae serve as bright standard candles. These stellar explosions reach a consistent peak brightness, allowing astronomers to estimate distances across hundreds of millions or billions of light years. When a supernova occurs in a distant galaxy, its brightness indicates the galaxy's distance. After fading, astronomers measure the galaxy's distance directly, at the universe's furthest edges. Redshift becomes essential. As space expands, light from distant galaxies stretches into longer, redder wavelengths. The more distant the galaxy, the faster it appears to recede, increasing its redshift. Measuring this redshift helps scientists infer how much the universe has expanded since the light left the galaxy. Using models of cosmic expansion, they convert redshift into an approximate distance, valuable for mapping large-scale structure, even if less precise for individual measurements. Another technique is gravitational lensing, where massive objects like galaxy clusters bend and magnify light from objects behind them. The degree of bending and pattern of the lensed images help estimate the distances to both the lens and the background object. These methods complement each other, creating a cosmic ruler and clock system, each suited for different scales. From nearby stars to billions of light years away, astronomers have developed an interconnected toolkit to measure cosmic distances. This network of methods allows us to understand the universe's size, age, and expansion. They turn light into a highway of information, revealing the universe's vastness and the forces shaping it. As technologies improve, our ability to measure and interpret light advances, continually expanding our understanding. These methods help decode the universe's mysteries, transforming faint distant light into a roadmap of cosmic history. They demonstrate how human ingenuity overcomes the constraints of scale, turning the faint glow of faraway objects into profound insights about the universe. By combining parallax, standard candles, redshift, and gravitational lensing, astronomers create a comprehensive picture of the universe's structure and growth. This ongoing pursuit pushes the boundaries of knowledge, revealing the universe's secrets and our place within it. The light from distant objects is more than illumination. It's a key to understanding the vast cosmos that surrounds us. Word count 501. Think about this. When we look up at the night sky, the stars we see might actually be thousands, millions, or even billions of light years away. But what exactly does that mean? How can these tiny points of light be so incredibly distant? And why do we bother measuring such vast distances in terms of light years instead of miles or kilometers? A light year is not a unit of time. It's a measure of distance. Specifically, it's the distance that light travels in 1 year through the vacuum of space. Since light zips along at an astounding speed of about 186,282 miles per second, or roughly 300,000 kilometers per second, it can cover an extraordinary amount of space in just a single year. Multiply that by 12 months, and you're talking about millions of miles every single day. Over the course of a year, that adds up to about 6 trillion miles, roughly 94 trillion kilometers. That's a mind-bogglingly vast distance, and it's why scientists use light years to describe the positions of stars, galaxies, and other celestial objects. Imagine shining a flashlight across the universe. If you could somehow keep it shining for an entire year at full power, the distance the light travels during that time would be a little over 6 trillion miles. That's 1 light year. When astronomers say a star is, say, 10 light years away, they're floating in a universe where distances are so immense that traditional units like miles or kilometers quickly become unwieldy. Instead, using light years makes the numbers more manageable and meaningful. But why does this matter beyond just crunching numbers? When we observe distant objects in space, we're actually looking back in time. Think about it. The light from that star takes 10 years to reach us. That means we see the star as it was 10 years ago, not as it is today. The farther away an object is, the further back in history we're peering. This is like having a time machine that shows us the universe's past. Every light year adds a little delay, letting us observe snapshots of cosmic history that span billions of years. This concept revolutionizes our understanding of the universe. It means that when astronomers look at a galaxy a billion light years away, they're witnessing an image of what that galaxy looked like a billion years ago, long before humans even existed on Earth. It's as if the universe is playing a giant cosmic slideshow that we can slow down or speed up based on how far away the objects are. Light years also help scientists chart the universe's structure and evolution. They're crucial for estimating distances to far-off galaxies and understanding how the universe is expanding. By measuring how light shifts and how objects move, scientists can piece together the story of the cosmos, from its fiery birth in the Big Bang to the intricate web of galaxies spread across the vast stretch of space. In essence, the concept of a light year bridges the enormity of cosmic distances with our curiosity. It transforms incomprehensibly vast stretches of space into numbers we can grasp and relate to. And more than that, it allows us to peer into the universe's past, uncovering stories written in starlight across billions of years. It's a tool that turns the universe's scale from mind-boggling to meaningful, giving us a way to measure, understand, and explore the universe that surrounds us. Measuring the distance to stars many light years away is a challenge. Even spacecraft would take thousands or millions of years to reach such stars. Astronomers therefore rely on methods like parallax and standard candles to determine cosmic distances. Parallax is familiar from holding a finger in front of your face. When you move your head, the finger appears to shift against distant objects. In astronomy, parallax involves Earth's orbit around the Sun. As Earth moves, our viewpoint changes, making nearby stars seem to shift position relative to distant stars. This apparent shift, the parallax angle, can be measured precisely. Using simple trigonometry and knowing Earth's orbit size, astronomers calculate a star's distance accurately for stars within a few thousand light years. Imagine a line from Earth to a star. When Earth is at one point in its orbit, the star appears in one position. 6 months later, from the opposite side, the star appears shifted relative to background stars. The smaller the parallax angle, the farther away the star. While elegant, this method works best for nearby stars because beyond a few thousand light years, the shifts become too tiny to measure directly. Nonetheless, parallax remains a fundamental direct method for nearby star distances, independent of assumptions. For stars farther away, parallax shifts are too small. That's where standard candles come in, our cosmic flashlights. Standard candles are objects with known true brightness, or intrinsic luminosity. By comparing their apparent brightness, how bright they look from Earth, to their known true brightness, we can find their distances. Picture shining a flashlight on a wall. The closer it is, the brighter it appears, the farther, the dimmer. Knowing the flashlight's true brightness allows you to estimate its distance from brightness alone. Similarly, certain stars and objects serve as standard candles. Cepheid variable stars are among the most important. They pulsate regularly, and scientists discovered a tight relationship between their pulsation period and their intrinsic brightness, the period-luminosity relation. By measuring the period of a Cepheid's pulsations, astronomers determine its true luminosity. Comparing this with how bright it appears from Earth yields its distance. Cephiids are luminous enough to be observed in galaxies millions of light years away, making them essential for mapping larger scales. Type Ia supernovae are another type of standard candle. These supernovae result from white dwarf stars reaching a nearly uniform peak brightness, regardless of their location. When a supernova occurs, astronomers measure its apparent brightness. Knowing its intrinsic brightness allows precise calculation of the distance to the galaxy hosting it. Together, parallax and standard candles form our cosmic distance ladder. Parallax provides direct, fundamental distances to nearby stars, which calibrate the luminosity of Cepheids. With Cepheids' true brightnesses understood, they serve as markers for measuring farther objects like other galaxies. Using Cepheids, astronomers detect even more distant events such as supernovae. This chain of measurements extends our reach farther into space. This layered approach enables us to measure the universe's vast scale, revealing the true distances to galaxies billions of light years away. From tiny positional shifts of nearby stars to flickering variable stars, we can chart the universe's expanse. These methods have revolutionized how we understand the cosmos, from a small collection of stars to a universe filled with billions of galaxies. The ingenuity of parallax and standard candles allows us to explore the universe's true size and structure. They turn faint starlight into a detailed cosmic map, unlocking the profound scale of the universe. Measuring the vast distances between galaxies is a significant challenge in astronomy. Imagine trying to gauge something so enormous that even stars appear as flickers of light in an unfathomable void. The scale of these cosmic expanses pushes our measurement techniques to their limits, prompting scientists to develop ingenious methods to decode the universe's grand tapestry. One major hurdle is space's emptiness. Light, travelling at about 300,000 kilometers per second, takes millions or billions of years to cross the gaps between galaxies. When we observe distant galaxies, we're looking so far back in time that the light reaching us may be billions of years old. This means our measurements are as much about history as they are about space itself. It's like peering through a cosmic time machine, complicated by the universe's constant evolution. A key challenge involves the absence of a universal yardstick across all scales. Nearby stars allow for straightforward distance measurements through parallax, which observes how an object's position shifts against distant background objects as Earth orbits the Sun. However, this method becomes ineffective for galaxies millions of light years away because the apparent shift is so tiny it's beyond current measurement capabilities. It's akin to detecting the movement of a tiny dot from miles away, nearly impossible with existing technology. To bridge this gap, astronomers use standard candles, objects with known intrinsic brightness. Cepheid variables and Type Ia supernovae serve as cosmic flashlights, allowing estimates of distance based on their observed brightness. But these methods also have uncertainties. Interstellar dust can dim their light, making objects seem farther than they truly are. Calibration across different galaxies demands careful comparison and assumptions, introducing margins of error. Redshift offers another approach. As galaxies recede due to space's expansion, their light is stretched toward the red spectrum. Measuring this redshift allows astronomers to estimate how fast a galaxy is moving away. With models of cosmic expansion, they infer the galaxy's distance. Yet this relies heavily on understanding the universe's expansion rate, something still being refined. Slight variations in the Hubble constant can significantly alter distance calculations, adding uncertainty. Cosmic dust and intervening matter further complicate measurements. Dust scatters and absorbs light, obscuring observations. Dark matter halos around galaxies can bend light via gravitational lensing, magnifying or distorting a galaxy's appearance. This effect makes it more difficult to determine the true size and brightness of distant objects. Additionally, the universe's dynamic nature complicates measurements over cosmic timescales. Galaxies merge, collide, and evolve, reshaping the cosmic web of filaments and voids. These changes mean that assumptions based on current observations may not hold in the distant past or future, adding complexity to estimating the universe's true scale. All these factors form a complex puzzle, requiring astronomers to piece together multiple lines of evidence, cross-validate various methods, and accept inherent uncertainties. The further we attempt to measure into the cosmos, the more mysteries unfold, extending our understanding and our limits into the unknown. Imagine you're standing on a quiet hilltop, gazing up at the night sky. You see a star shining, its light travelling through the vast emptiness of space, journeying across unimaginable distances. But how do astronomers even begin to quantify these colossal gaps? How do they measure something so vast that it defies our everyday understanding of distance? The answer lies in a unit called the lightyear, a measure so precise yet so mind-boggling that it stretches the limits of our imagination. Mathematically, a lightyear is simply the distance that light travels in 1 year through a vacuum. To understand this, we need to recall the speed of light, which is approximately 300 million meters per second. That's a figure so vast that it's almost impossible to truly grasp. Light zipping around the Earth's equator about 7.5 times in just 1 second. But in the context of an entire year, that speed accumulates into something extraordinary. Breaking it down, 1 year spans about 315,696,000 seconds. If you multiply that number by the speed of light, you get the total distance covered by light in a year. Mathematically, it looks like this. Distance of a light year, speed of light x duration of 1 year, expressed numerically, dien-dasi ext. Where? Joules is the distance travelled by light in 1 year, the light year. This is the speed of light in a vacuum, approximately 300 million meters per second, or about 3 times 10 to the power of 8 meters per second. That is the length of 1 year in seconds, roughly 315,696,000 seconds. Plugging in these numbers, d turns to 3 10⁸ meters a second, x 3,596 x 10⁻⁷ seconds. When we carry out that multiplication, The distance comes out to about 9.492 trillion kilometers, or roughly 6.23 trillion miles. That's a figure so enormous that it challenges our everyday sense of distance. Why use light years? Because it takes light a whole year to cover that stretch. That means when astronomers look at a star that's 100 light years away, they're seeing the star as it was 100 years ago. Light from that star has travelled all that way across space to reach us now. This not only frames the staggering scale of the universe, but also gives us a cosmic clock to look back in time. So, at its core, a light year is a simple concept. It's just the distance light travels in a year, calculated with a straightforward formula. But when you consider how far that really is, it turns our familiar notions of distance inside out, reminding us just how expansive and mysterious the universe truly is. A light year isn't a measure of time, it's a measure of distance. That might seem a bit confusing at first because of the word year, which is typically associated with time, but in the context of a light year, it refers to how far light travels in 1 year. To understand why, let's unpack what a light year really is. Imagine standing under a clear night sky, gazing at the stars. Some of those twinkling points of light are thousands, or even millions of light years away. When astronomers say a galaxy is, say, 10 million light years away, they're not implying it took 10 million years to get there. Rather, they're describing how far away it is in terms of how far light can travel in that span of time. Light moves at a staggering speed, about 300,000 kilometers per second. That's fast enough to circle the Earth more than 7 times in a single second. Over the course of a year, specifically around 315,600 seconds, that speed adds up to roughly 9.4 trillion kilometers. We call this distance 1 light year. So the reason it's a measure of distance, not time, hinges on what the term light year actually captures: the length of the journey light makes over 1 year. Think of it as a yardstick laid out in the universe, measuring how far light travels in that amount of time. It's a convenient way for astronomers to express vast cosmic distances without resorting to endless zeros or awkward fractions. If a galaxy is 1 billion light years away, it means the light we see today from that galaxy left there 1 billion years ago. We're observing the galaxy as it was, long before our time, because that's how long the light took to reach us. The universe is so immense that even light, the fastest thing in existence, takes eons to traverse its vast stretches. Using a light year helps us visualize these immense scales without resorting to superhuman mental calculations. Saying, a galaxy is 10 billion kilometers away isn't very intuitive, because 10 billion kilometers, while large, is tiny compared to the hundreds of quintillions of kilometers that make up the distance light travels in a year. By translating these distances into light years, we can grasp just how far away objects are in terms that scale with the universe itself. It's similar to how miles or kilometers work on Earth. These are units designed to measure distance, not time. The distinction becomes clearer when we realize that no matter how fast you go, you can't travel faster than light. Therefore, when astronomers talk about something being separated by several light years, they're describing the space between 2 points, not how long it takes to get from one to the other. In essence, calling it a light year anchors our sense of distance to a universal constant, the speed of light, giving us a common language to describe the boundless universe. It's a way of saying, this is how far light can go in a year, which helps us understand the scale of everything around us. And it's this simple yet profound concept that opens our eyes to just how vast, mysterious, and mind-boggling the cosmos truly is. The concept of a light year helps us grasp the vastness of the universe. It's like a cosmic measuring tape, giving scale to distances that stretch across space, making them more comprehensible. A light year isn't just a unit, it's a way to understand how far light travels in 1 year. Since light moves at about 186,182 miles per second, it can circle the Earth roughly 7 times in a second. Over a year, around 31,684,000 seconds, that adds up to about 6 trillion miles. That's unimaginably vast, especially when these distances are stacked end to end. For example, the nearest star system, Alpha Centauri, is about 4.3 light years away. The light we see from it today left over 4 years ago, carrying a story from the past. This means when astronomers observe distant objects, they see them as they were when the light first set out. The farther an object, the longer its light takes to reach us. We're essentially looking back in time, seeing the universe as it was years, even billions of years ago. This concept rewrites how we perceive cosmic distances. Spaceship explorers might think about travel time, but for us, light years represent cosmic memories encoded in photons. Our own galaxy, the Milky Way, spans about 100,000 light years across. When we look up, the light from stars has travelled thousands of years before reaching our eyes. Some stars we see are already gone, their light just arriving now. The universe is like a vast tapestry woven with threads of light travelling across unimaginable distances. Without the idea of a light year, comprehending this scale becomes nearly impossible. Beyond individual stars and galaxies, light years help measure larger cosmic structures. Quasars, which are bright, energetic centres of distant galaxies, can be billions of light years away. Observing them lets us see back billions of years into a young universe. Their flickering light provides crucial insights into cosmic evolution, revealing how the universe developed over vast spans of time. Cosmologists also use light years to chart the universe's expansion. They map the distribution of galaxies and matter across unimaginable distances. The Hubble Space Telescope has captured images of galaxies over 10 billion light years away. The light from these galaxies left when dinosaurs roamed Earth, an almost unfathomable stretch of space and time. The farther the light has travelled, the deeper into the universe's history we are peering. The beauty of the light year is in how it turns the universe's immense scale into an understandable framework. It helps measure and estimate the universe's history and evolution, from our nearby stars to the most distant galaxies. It's a reminder that in the cosmos, distances are more than numbers. They are stories waiting to be told, echoing across space and time. By understanding these distances, we connect more deeply to the universe's timeless story. The vastness of space becomes less abstract when we think in terms of light years. It's a measure of cosmic memory, revealing how light travels through billions of years and billions of miles. Light years offer a way to bridge the gap between human perception and the universe's immense scale, bringing the cosmos closer to us, one photon at a time. Imagine trying to grasp the sheer scale of a light year. The distance light travels in 1 year, which is about 6 trillion miles or nearly 10 trillion kilometers. It's almost impossible for our minds to truly comprehend something so vast. When we think about a single light year, we're talking about a distance so enormous that it stretches the limits of our intuition and perception. It challenges us to stretch beyond everyday experiences, where distances are measured in miles or kilometers, into a universe so expansive that words often fall short of capturing its scale. To imagine a light year, you might think of it as shining a flashlight in the dark. Light travels at about 300,000 kilometers per second. In 1 year, that light covers a distance so immense that if you were to compare it to the size of Earth, it would circle our planet's equator about 75 times in just 1 second. These figures are astounding, but even they don't fully grasp the mind-bending reality. They're just distant numbers until you start to visualize them in context. Thinking of space in terms of light years makes the universe seem both almost infinite and profoundly distant. When astronomers tell us that a galaxy is 1 billion light years away, that means the light we see today left that galaxy 1 billion years ago. We're peering into the past every time we look at distant stars and galaxies. It's as though we're looking through a cosmic time machine, seeing the universe as it was, not as it is right now. This idea boggles the mind because it implies that the past is still visible to us, frozen in the light that took eons to reach our eyes. This concept also pushes the boundaries of our perception of time and space. We're used to thinking of distances as something we can traverse or measure directly, but the scale of light years reminds us that some parts of the universe are utterly beyond our reach, literally light years away. To travel even a few light years would require a journey that spans generations, perhaps centuries or even longer with our current technology. It makes space travel seem almost impossible within a human lifetime, emphasizing how distant and isolated these cosmic realms are. Imagining a light year challenges our perception of the universe as a place of immediate familiarity. It forces us to accept that much of what we observe is evidence of events long past. When we gaze up at the night sky, we are looking back in time. Each point of light is a message from the past, a universe that existed millions or billions of years ago, so distant that it's almost as if space is a vast cosmic memory book. This perspective compels us to think differently about our place in the universe. It highlights how tiny and transient our existence is relative to the grand cosmic scale. The idea of light years stretches our mental frameworks and confronts us with the reality that the universe's true nature is far more immense and mysterious than our everyday experience suggests. It's a humbling reminder of the universe's boundless scale, a scale that, in many ways, breaks the limits of our minds. When exploring the vastness of space, understanding measurement units is essential to grasp the enormous distances involved. Light years are among the most widely used units, but they are part of a larger set of measurements that help astronomers map the universe effectively. Comparing light years to other units reveals how our perception of cosmic distances evolves from familiar scales to the almost incomprehensible sizes of interstellar and intergalactic space. The most common unit used within our solar system is the astronomical unit, AU. 1 AU equals approximately 150 million kilometers, the average distance from Earth to the Sun. This unit is practical for measuring planetary orbits, asteroid distances, and other objects within our solar neighbourhood. However, when we consider stars beyond the solar system, the AU becomes too tiny to be meaningful. For example, Proxima Centauri, our closest stellar neighbour, is about 4.2 light-years away, roughly 40 trillion kilometres. Expressing such vast distances in AU is impractical. It would require an enormous number of AUs, highlighting their limitations at interstellar scales. To bridge this gap, astronomers use parsecs, a unit based on stellar parallax measurements. 1 parsec equals approximately 3.26 light-years, or about 3.16 trillion kilometers. The term derives from parallax second, reflecting how stellar positions are measured via Earth's orbit to determine distances. Parsecs are especially useful in galactic astronomy because they directly relate to parallax observations, offering a more practical measure of star distances than light-years over large scales. For instance, the Milky Way's diameter is about 100,000 light-years, equivalent to roughly 30,000 parsecs. This scale makes parsecs invaluable for mapping and understanding our galaxy's structure. When examining larger cosmic structures such as galaxy clusters, superclusters, or the overall universe, light-years prove to be more intuitive and meaningful. The Andromeda Galaxy, our nearest major galactic neighbour, is approximately 2.5 million light-years away. Distance is so immense that expressing them in kilometres involves countless zeros. The size of the observable universe extends roughly 46 billion light-years in every direction, encompassing everything from the earliest galaxies to cosmic background radiation. Cosmologists often adopt even larger units, like gigaparsecs, billions of parsecs, to describe these enormous scales accurately. These units facilitate understanding the universe's expansion, its origins, and large-scale structure. The use of light-years and similar measurements underscores how our perspective on distance expands with scale. Light-years offer a tangible sense of how far light travels in a year, an almost poetic way to visualize cosmic journeys. Parsecs, kiloparsecs, and gigaparsecs help contextualize the universe's architecture. From close stars to the vast intergalactic voids, each measurement has a distinct purpose. Light-years for understanding photons' travel times, parsecs for star distances, and gigaparsecs for the universe's overall size. These units serve as essential tools, guiding us through the cosmic landscape. Ultimately, these measurement units emphasize how small we are within an unfathomably large universe. They also reveal how our knowledge has evolved, helping us make sense of distances that once seemed beyond comprehension. By translating enormous stretches of space into units like light-years and parsecs, astronomers provide us with a lens, imperfect yet profound, to understand our place in the vast cosmos. They turn the seemingly unmeasurable into comprehensible scales, allowing us to ponder the universe's grand design and our own tiny existence within it. The speed of light is considered a fundamental constant because it is woven into the fabric of our universe, defining how the cosmos operates at a fundamental level. Unlike most speeds we encounter daily, such as a car racing down the highway or a bird flapping its wings, the speed of light in a vacuum remains unwavering, no matter where or when it is measured. It clocks in at approximately 300,000 kilometers per second, about 382 miles per second, and does not change, even if you are moving towards or away from the light source. This unchanging nature leads to profound implications. It challenges our classical understanding of speed, which was based on the idea of an absolute medium, ether, through which light travelled, similar to sound waves through air. However, late 19th century experiments like Michelson-Morley showed that light's speed remains constant regardless of the observer's motion or the light source's movement. This pointed to a universal constant independent of relative motion, reshaping our understanding of physics. The constancy of light speed is central to Einstein's theory of special relativity. One key revelation is that the laws of physics are the same for all observers, regardless of their motion. If light speed varied with the observer's frame of reference, the laws would be inconsistent, making reliable universe-wide predictions impossible. By assuming a fixed speed of approximately 300,000 km/sec, Einstein unified space, time, and motion into a coherent framework. This led to the realization that measurements of time and length are relative, changing with the observer's velocity. Concepts like simultaneity and causality depend on this invariant speed, fundamentally altering our understanding of reality. The speed of light also sets the universe's ultimate speed limit. Nothing can travel faster than light through empty space because doing so would require infinite energy. This cosmic speed cap is a core law of physics, influencing how signals propagate across the universe and how we interpret cosmic expansion. The invariant speed ensures that causality and the sequence of events remain consistent throughout the universe. Moreover, the universal nature of the speed of light makes it essential in measuring cosmic distances. It gives rise to the concept of a lightyear, the distance light travels in 1 year, allowing astronomers to gauge the vastness of space. Since the speed remains steady, distances to stars, galaxies, and the observable universe can be accurately determined. For example, observing a galaxy 10 billion light-years away means seeing it as it was 10 billion years ago, because light takes that long to reach us. This finite travel time shapes our understanding of the universe's history and scale. In a universe governed by the constancy of the speed of light, there exists a sense of cosmic harmony, where the fundamental properties of reality are fixed and unchanging. These constants serve as anchors, creating a coherent framework for physics, astronomy, and cosmology. The speed of light isn't just a number, it's a foundational pillar that influences the structure of space and time itself, ensuring the universe operates in a consistent and predictable manner. 505 words. Imagine standing in a vast open field at night, holding a mirror and a stopwatch, trying to measure something seemingly impossible: how fast light travels. Thousands of years ago, early astronomers thought light was instantaneous, as they couldn't imagine a finite speed for something so bright and swift. It wasn't until the 17th century that humans began to understand light's cosmic speed limit. One of the earliest attempts was by Galileo Galilei, who wondered if light took time to travel from the sun to Earth. He set up an experiment with 2 lanterns on distant hilltops, uncovered them simultaneously, and hoped to measure the delay. However, the distance was too short, and light's speed was so fast that no delay was detectable to untrained eyes. Galileo believed, temporarily, that light might be infinitely fast because he saw no measurable lag. By the 19th century, advancements allowed for more precise measurements. Ole Rømer, a Danish astronomer, made a breakthrough around 1676. Observing the eclipses of Jupiter's moon Io, he noticed their timing shifted depending on Earth's position relative to Jupiter. When Earth was closer, eclipses happened earlier. When farther, they were delayed. Rømer concluded this was due to the finite speed of the light. The time it took for light from the eclipse to reach Earth varied with distance. From his data, he estimated that light took about 20 minutes to cross Earth's orbit, which he used to approximate the speed at roughly 186,000 miles per second. This was an astonishing achievement, bringing humanity closer to understanding how fast light truly is. Later, scientists refined Rømer's method. In 1849, French physicist Armand Fizeau performed a terrestrial experiment using a rotating toothed wheel, directing a beam of light toward a distant mirror. When the wheel spun at just the right speed, the teeth would block the returning beam. By measuring the wheel's rotation rate and the known distance, Fizeau could calculate the speed of light more precisely. His experiment moved us closer to the actual value and provided a significant step forward. In 1862, Léon Foucault improved this approach with a rotating mirror setup, yielding more accurate measurements. Over time, these experiments confirmed that light travels at approximately 186,282 miles per second, aligning with today's accepted value. Each step, Galileo's early guesses, Reaumur's celestial observations, Fizeau's terrestrial experiment, and Foucault's refinements, gradually revealed the incredible speed of light. These discoveries transformed our understanding. Initially, light was thought to be instantaneous. Then scientists realized it had a finite speed, measured in fractions of a second across billions of miles. From wondering whether light had a speed to knowing it with incredible precision, humanity's progress is remarkable. It's awe-inspiring that some of history's sharpest minds worked so hard to measure something so fast that, to understand it fully, they needed to think in terms of fractions of a second over vast distances. The journey from Galileo's tentative experiment to Foucault's refined measurements highlights the power of scientific progress. Despite its incredible speed, light's velocity remains a cornerstone of physics, shaping our entire understanding of the cosmos. The quest to measure how fast light travels has been a testament to human curiosity and ingenuity, propelling us from speculation to precise knowledge, and forever changing our view of the universe. Imagine a universe where nothing can travel faster than light. That tiny, seemingly inconsequential speed limit is actually the backbone of the cosmos as we know it. It shapes everything from how galaxies cluster to our understanding of time itself. This ultimate speed limit isn't just a quirky rule, it's woven into the fabric of reality, with profound implications that challenge our perceptions. First, the idea that light speed, roughly 300,000 kilometers per second, is the universe's fastest speed rules out faster than light travel and communication. This significantly affects how we think about moving through space. In science fiction, faster than light travel may seem possible, but in reality, it would take an unthinkable amount of time to reach distant stars. Even the nearest star system is several light years away, so travel would span years or more. This limit keeps civilizations separated at a cosmic scale, making distant worlds more like distant lands separated by huge, unbridgeable distances. The implications go deeper, because no information can travel faster than light. Causality, the relationship between cause and effect, is preserved. If information exceeded this limit, the cause and effect chain that underpins the universe could break down. Events might become ambiguous or paradoxical, with effects seemingly preceding causes. Such scenarios threaten the logical structure of physics, risking chaos and inconsistency. The universe depends on this speed limit to keep reality predictable. It keeps the past fixed, the present meaningful, and the future causally connected. The speed of light also affects how we perceive time. According to Relativity, as you approach light speed, time slows down for you relative to stationary observers. At the speed of light, the equation suggests time would stop entirely for you. This isn't a mere curiosity. It indicates that time's flow is intimately tied to the speed limit. The universe's structure relies on this interconnectedness, affecting everything from star aging to galaxy evolution. Another consequence involves black holes and cosmic expansion. The speed of light defines the event horizon, the boundary beyond which nothing can escape. This limit helps characterize black holes and their intense gravitational pull. Additionally, the universe's expansion appears faster than light in some regions, but this doesn't violate the rule, as space itself stretches rather than objects moving through space faster than light. The finite speed of light also shapes our cosmic perspective. When we look into the night sky, we see galaxies as they were billions of years ago because their light takes that long to reach us. Each photon carries a message from the distant past, telling stories of a changing universe limited by light's speed. Our view of the cosmos is like a vast tapestry woven with photons from the past, always constrained by the speed of the light. Thus, the fact that light speed caps the maximum velocity isn't just a physics fact, it's a foundation of reality. It ensures order, maintains causality, and stretches our imagination. When we gaze at the stars, we're looking into the deep past, witnessing a universe that evolves within the bounds of this ultimate speed. It shapes everything from the behavior of particles to the evolution of galaxies and the structure of spacetime, making it a fundamental principle that governs all of existence. When discussing the universe and its vast distances, our understanding of the speed of light isn't just a number, It's fundamental to how we perceive reality. Einstein's theory of relativity transformed our view of motion, space, and time, revealing that the speed of light isn't just high, it's the ultimate speed limit of the cosmos. No object with mass can reach or exceed this cosmic barrier. This limit has profound implications, especially when considering the enormous gaps between galaxies or the fleeting moments of cosmic events. Before Einstein, many scientists thought space and time were separate and absolute, fixed stages on which the universe unfolded. But Einstein's special relativity combined them into a single fabric called spacetime. Approaching the speed of light causes strange effects. Time appears to slow down for objects moving near light speed. For example, astronauts travelling close to light speed experience less passage of time compared to someone on Earth. To the astronauts, only a short time passes. To someone on Earth, their clocks seem to tick more slowly. This phenomenon isn't just mathematical. It's confirmed by experiments with particles travelling at near-light speeds and atomic clocks on airplanes. Mass and energy are linked through Einstein's famous equation E=mc2. As an object accelerates toward light speed, its energy requirement increases exponentially, approaching infinity. This makes it impossible for any object with mass to reach or surpass the speed of light. Light, which has zero rest mass, travels at this universal maximum speed unaffected by its energy or source. It's as if the universe has put an unbreakable speed limit in place. Nothing with mass can catch or go faster than light. This shifts our understanding of the universe significantly. It establishes causality, the cause and effect chain that keeps the universe logical. No information, matter or energy can travel faster than light, ensuring effects cannot occur before their causes. This preserves the chronological order of events and the universe's overall coherence. The finite speed of information transmission is fundamental to the universe's structure, ensuring distant regions can't influence each other instantaneously. Watching light from distant galaxies means we're seeing them as they were in the past, millions or billions of years ago. Because nothing can travel faster than light, our ability to communicate or send signals across cosmic distances is limited by this universal speed cap. The universe effectively enforces a strict cosmic speed limit on travel and communication, shaping the potential for exploration. This concept is challenging to grasp because it contradicts everyday intuition, where speeds can be anything, cars, planes, rockets, without the constraints of relativity. Nevertheless, these insights are crucial for understanding phenomena like black holes, cosmic expansion, and the cosmic microwave background, the faint echo of the universe's fiery beginnings. The universal speed limit set by light governs not just stars and galaxies, but also the fabric of causality, space, and time. It reveals a universe that is far more interconnected and constrained than our daily experiences suggest, fundamentally shaping our understanding of reality and the cosmos. The idea of something travelling faster than light has fascinated scientists, science fiction writers, and curious minds for generations. But despite the allure of breaking such a fundamental cosmic speed limit, current physics shows that nothing can surpass light in a vacuum. Let's explore why this is. Albert Einstein's theory of special relativity established that the speed of light, about 186,282 miles per second, is the ultimate speed limit for anything carrying information or matter. As an object accelerates closer to this speed, its relativistic mass effectively increases, making it seem heavier from an outside perspective. To reach light speed, it would require an infinite amount of energy, which is impossible with any known form of energy or propulsion. Think of trying to push a car that gets heavier as you push. Ultimately, it becomes impossible to keep going. This limitation isn't just about energy, it's woven into the very fabric of space-time. The theory predicts no signal or particle with mass can reach or exceed the speed of light because it would violate causality, the principle that cause precedes effect. If faster-than-light travel were possible, it could lead to paradoxes like receiving messages before they're sent, causing logical contradictions in reality. There are particles called tachyons, hypothetical entities postulated to always travel faster than light. However, if tachyons exist, they would have strange properties, such as imaginary mass, and could violate causality. So far, experiments have found no evidence of tachyons. Their existence remains speculative and outside confirmed physics. Some phenomena seem to challenge the idea that nothing can travel faster than light, but they don't violate the speed limit. Quantum entanglement, for instance, involves two particles connected in a way that a change in one instantly affects the other, regardless of distance. This is called spooky action at a distance, but it doesn't allow faster-than-light communication, as no information travels through entanglement. It's a mysterious connection that respects relativity laws. The expansion of the universe offers another example. During the Big Bang, space-time expanded faster than light during cosmic inflation. No objects moved through space faster than light. Rather, space itself was stretching rapidly. This causes objects to recede from each other at superluminal speeds, but no object is moving faster than light through space. It's space-time that's expanding. All of these points indicate a universe where the speed of light remains an insurmountable barrier for matter and information, a cosmic speed limit embedded deeply in physics. This boundary maintains the universe's consistency and causal structure. For now, breaking the light speed barrier belongs to science fiction. It's an exciting frontier that continues to inspire our understanding, but current scientific laws make it impossible to surpass this universal limit. Imagine shining a flashlight across a dark room. When you flip the switch, the light races across the space between you and the wall at about 300,000 kilometers per second. This finite speed isn't just a fact, it's the reason we can connect time and distance in the universe. The speed of light acts as a cosmic ruler, shaping how we measure vast distances and understand cosmic history. Astronomers observe the night sky by looking back in time. Because light takes time to travel, the distance to a star or galaxy isn't just about how far away it is, but also how long ago the light left that object. A star 10 light years away means we see it as it was 10 years ago. A galaxy a billion light years away means viewing it as it was a billion years in the past, when the universe was young. This link between distance and time flips our everyday intuition. On Earth, viewing objects across a mountain or down a street shows their current state. But in space, our observations are snapshots of the past, long gone from the present moment. Everything we see is a story written long before the light reaches us. Take the cosmic microwave background radiation, the oldest light detectable. It floods the universe from every direction, dating back nearly 13.8 billion years. Because that radiation took so long to reach us, it offers a glimpse into the universe when it was just 300,000 years old, an instant in cosmic history. The finite speed of light makes this possible, allowing us to study the universe's earliest moments. This relationship also influences space travel and communication. Even if a spaceship could travel at light speed, something current physics says is impossible, it would still be limited to that universal speed limit. Sending a spacecraft to a star 10 light years away would take 10 years, just as long as the light took to reach us. For distant galaxies, travel times could span billions of years, making such journeys unattainable for humans within a lifetime. The finite speed of light shapes our understanding of the universe's age and the development of cosmic structures. Light from supernovae, gamma-ray bursts and quasars helps trace the universe's expansion history. By measuring their brightness and distance, we can infer how quickly space itself is stretching apart, informing models of cosmic evolution. Thus, the cosmic speed limit isn't merely a boundary, it's a bridge linking space and time. It reveals that distances also represent different epochs in history. When we observe distant objects, we're seeing a universe that isn't static or current, but woven with threads of the past. Each photon carries the story of a long-gone era. In summary, the finite speed of light is fundamental to our understanding of the cosmos. It connects how far away objects are to how long ago their light began its journey. This relationship makes the universe a vast unfolding storybook, where each observation opens a window into a different moment of cosmic history. Our universe is a tapestry woven with light, revealing its deep, ancient past through the signals that travel across the fabric of space and time. When we look out into the universe, we're not just gazing at distant objects. What we're truly doing is peering back in time. Imagine shining a flashlight across a vast canyon. The light takes a moment to reach the other side. Similarly, light from stars and galaxies takes years, sometimes billions of years, to travel across cosmic distances to reach us. The farther away an object is, the longer its light has been travelling before it arrives in our telescopes. This means when we observe a galaxy that's a billion light years away, we're seeing it as it was a billion years ago, not how it looks today. This concept is like having a cosmic time machine. Every photon that lands in our instruments is a messenger from the past. carrying with it a snapshot of what the universe looked like at the moment that light was emitted. When astronomers study these ancient signals, they're essentially opening a window into the universe's history, allowing us to witness the formative years of galaxies, stars, and planetary systems. It's as if by looking deeper into space, we're also looking farther back in time, uncovering the story of cosmic evolution from the dawn of the universe. The importance of this perspective becomes crystal clear when trying to understand how the universe has changed over billions of years. For example, when observing distant galaxies, astronomers see young, chaotic systems with active star formation, unlike many descriptions of nearby, more mature galaxies that have settled into a calmer, more structured state. This helps scientists piece together how galaxies develop over cosmic time, revealing processes that are impossible to mimic in laboratories here on Earth or to observe directly in real time within our own galaxy. Furthermore, this historic view sheds light on some of the universe's most profound mysteries. By observing objects from different epochs, astronomers can track changes in the expansion rate of the universe, test theories about dark energy, and better understand the Big Bang itself. For instance, by studying the cosmic microwave background radiation, the oldest light in the universe, and comparing it with observations of distant supernovae and galaxy clusters, scientists gain clues about the universe's infancy and its accelerated expansion. Looking back in time also underscores just how vast and dynamic the universe truly is. It reveals that the universe we see today is constantly evolving, reborn through continuous cycles of star birth and death, galaxy collisions, and cosmic expansion. The distant universe, seen through light that has travelled eons, is like a giant historical archive, storing the chronicles of everything that has happened ever since the universe's earliest moments. In this way, every distant galaxy we observe serves as a chapter in a grand storybook written across the cosmos, each one telling us about a different time, different conditions, and different stages of cosmic growth. It's a humbling reminder that when we gaze into the night sky, we're not just looking outward, we're also looking backward in time, uncovering the universe's deepest secrets and our own origins amidst the stars. When we look up at the night sky and observe distant galaxies, stars, and cosmic phenomena, we're essentially looking back in time. Because light takes time to travel through the vast cosmos, every image we see is a snapshot of the past, sometimes millions, even billions of years old. The light from a galaxy 2 billion light years away left that galaxy 2 billion years ago, an era when the Earth was still in its infancy and the universe was vastly different. This notion that observing distant objects is like peering into history sparks a sense of wonder and curiosity. It's as if the universe has become its own cosmic time machine, allowing us to witness events that happened eons before humans ever walked the Earth. When astronomers detect a supernova explosion in a galaxy millions of light years away, what they're actually witnessing is the bright aftermath of an event that took place eons ago. The explosion might have happened when dinosaurs still roamed Earth, or even earlier, long before our species emerged. This time delay due to light's finite speed means that much of our understanding of the universe's history relies on interpreting the light arriving at our telescopes. Scientists study the light's properties, its spectrum, intensity, and variations over time, to decipher what occurred during those ancient events. The light carries valuable information about the physical conditions, chemical compositions, and velocities of distant objects at the moment the light was emitted. When looking at the cosmic microwave background radiation, the faint glow left over from the early universe, scientists are peering back roughly 300,000 years after the Big Bang. This radiation is the universe's baby picture, providing clues about the universe's infancy, moments after its fiery birth. By analysing how the pattern of tiny temperature fluctuations in this glow manifests, cosmologists can piece together what the universe was like when it was a mere fledgling, and how it has evolved over billions of years. Similarly, observations of galaxies at different distances reveal a timeline of cosmic evolution. Nearby galaxies show us what the universe looks like today: spiral arms, star-forming regions, black holes, while distant young galaxies appear much more chaotic and energetic. They are the universe's adolescents, still forming their structures, bursting with star formation, and host to many more of those luminous quasars that powered the early cosmos. Sometimes, cosmic events observed today are not just distant echoes, but are occurring right now in the distant parts of the universe, out of reach for direct human perception. Because universe expansion stretches light waves, It also causes the light from some of these distant phenomena to shift toward the red end of the spectrum, a process called redshift. This effect helps scientists determine how fast objects are moving away from us and how the universe itself is expanding. All of this ties into the fundamental relationship between space and time. The universe's history is written in the light reaching us from the edges of the observable cosmos. Every photon traveling through space acts as a messenger, carrying stories from long ago, stories that, when decoded, reveal how the universe has evolved from a hot, dense beginning to the vast, complex cosmos we observe today. Looking away is, in a sense, looking back, unraveling the mysteries of cosmic history one photon at a time. Imagine gazing up at the night sky, observing a distant galaxy. The moment your eye catches the light from that galaxy, you're seeing it as it was billions of years ago, not as it is right now. This phenomenon introduces two fascinating concepts in astrophysics: look-back time and light travel time. While they might sound similar, each offers a unique perspective on our cosmic observations and helps us piece together the history of the universe. Let's start with light travel time. It's a straightforward idea. It's the amount of time that light takes to travel from an object in space to our eyes or telescopes here on Earth. Think of it as the universe's postage stamp, sending information across vast cosmic distances at the universal speed limit, light speed, which is about 300,000 kilometers per second. For a galaxy a billion light years away, the light we see today left that galaxy a billion years ago. It's like receiving a postcard from the past, transported across the cosmic ocean in that tiny but immensely fast speed. Light travel time tells us how long ago the light was emitted. It's directly tied to the distance between us and the object, assuming the speed of light is constant across space-time. But while light travel time gives us a time delay, it's just one piece of the puzzle. The other concept, look-back time, takes a broader view. It's the time elapsed between the moment the light was emitted from an object and the moment we observe it, considering the history and expansion of the universe itself. When we observe a galaxy that is a billion light years away, the look-back time is roughly a billion years too. However, what makes the concept of look-back time so intriguing is that it incorporates the universe's expansion. Because space itself was smaller in the past, the actual age of the universe when that light began its journey is also a factor. Imagine the universe as a stretching fabric. Light from distant galaxies has to traverse this fabric, which has been expanding over cosmic time. As that fabric stretches, the distance between galaxies increases even as the light is on its way. When researchers calculate the universe's age or the formation time of distant objects, they use models that relate the observed redshift, the shift in light toward the red end of the spectrum due to expansion, to the look-back time. In this way, look-back time provides a temporal map of cosmic history, revealing how long ago particular events occurred, such as the birth of the first stars or the formation of galaxies. So, while light travel time is like the universe's stopwatch, counting how long it took the light to reach us, look-back time is more like a cosmic history book, telling us the story of how long ago events happened relative to today, factoring in the universe's expanding nature. Both are vital in astrophysics because they allow scientists to peel back layers of cosmic history, revealing an astonishingly detailed narrative of our universe's evolution, one that stretches back billions of years, a narrative written in the ancient light that finally reaches our telescopes. Light serves as our cosmic messenger, carrying the story of the universe from its very beginning, billions of years ago, directly to our telescopes. Think of space as a giant cosmic time machine. When we gaze at the night sky, we're looking back in time due to the finite speed of light. Light from distant galaxies, star nurseries, and supernovae takes years, sometimes billions of years to reach us. So, seeing a galaxy 100 million light years away means observing it as it was 100 million years in the past. Each photon is like a tiny postcard, offering a snapshot from different chapters of cosmic history. This ability turns speculation into a detailed chronicle of events shaping the universe. Detecting the faint glow of the earliest galaxies provides clues about how the first stars ignited, how galaxies formed and evolved, and how the universe's structure came to be. It's akin to peeling back layers of an enormous onion, revealing a timeline stretching from the Big Bang to today. Light also captures the universe's dynamic nature. Variable stars flicker, supernovae explode, and quasars flare, all observable through their emitted light. Studying these changing signals over time allows astronomers to measure how cosmic objects behave and evolve, providing insight into cosmic history. It shows that galaxies are not static islands, but entities that merge, evolve, and sometimes collide, reshaping our understanding of the universe's evolution. Another pivotal piece is the microwave background radiation, a faint afterglow from roughly 300,000 years after the Big Bang. This ancient light has travelled across the universe for over 13 billion years, offering a snapshot of the universe in its infancy, hot, dense, and chaotic. Analysing this radiation helps scientists understand how structures formed amid a nearly uniform early universe, giving us a glimpse into the tumultuous birth of cosmic time. Light also reveals the chemical composition of celestial objects. Spectral lines, signatures of elements, allow us to determine the makeup of stars, planets, and interstellar gas. This information informs us about stellar life cycles, planet formation, and the potential for life elsewhere, enriching our understanding of cosmic chemistry and evolution. Looking ahead, advances in telescopes like the James Webb Space Telescope will let us peer further back, closer to the universe's birth. Such observations may answer profound questions. How did the first galaxies form? What conditions existed just after the Big Bang? How did the cosmic web of matter develop from initial density fluctuations? In essence, light is the universe's storyteller. Each photon carries a message from the distant past, enabling us to reconstruct the grand saga of cosmic evolution. Without it, the universe's history would remain hidden in darkness, and our understanding of our origins would be vastly diminished. Thanks to the light, we can see the universe as it was eons ago, forging an extraordinary connection across space and time. It allows us to witness the universe's evolution, from its chaotic beginnings to the structured cosmos we observe today. The story told by light is fundamental for understanding how everything came to be, how cosmic structures grew, and how life might arise in this vast universe. Imagine looking up into the night sky and wondering, how long has this universe been here? That's a question that has fascinated humans for centuries, but how do scientists actually go about estimating the age of something so vast and distant? It's a puzzle wrapped in light, time, and lots of clever detective work. One of the key tools scientists use is the study of the oldest stars. These ancient stars, often found in spherical clusters called globular clusters, act like time capsules. By analysing the light emitted from these stars, astronomers can determine their composition, temperature, and brightness. Using models of stellar evolution, which describe how stars of different ages burn through their fuel, they can estimate how long these stars have been shining. When astronomers pinpoint the oldest stars, they get a lower limit for the age of the universe, because nothing can be older than the universe itself. But stars aren't the only clues. The cosmic microwave background, sometimes called the universe's baby picture, is a faint glow of radiation that fills the cosmos. This light is the residual heat from the Big Bang, travelling across space for nearly 13.5 billion years. When scientists measure the properties of this ancient light, they are essentially looking back in time to when the universe was a mere soup of hot, dense particles. The key to unlocking the universe's age with this cosmic microwave background is in the detailed measurements made by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft. These instruments analyse tiny fluctuations in the temperature of this radiation, which encode information about the universe's contents, dark matter, dark energy, normal matter, and how they evolved with time. By fitting these observations into our models of cosmology, scientists can calculate the expansion rate of the universe. That's where Hubble's law comes into play. Edwin Hubble discovered that galaxies are retreating from us, and the speed at which they do so is proportional to their distance. This relationship allows us to determine a Hubble constant, which essentially measures how fast the universe is expanding today. If we assume this expansion rate has remained relatively consistent over cosmic time, or understand how it has changed, we can work backwards to figure out how long it's been expanding. By combining the measurements of the Hubble constant with detailed cosmological models developed from the cosmic microwave background, scientists can estimate the age of the universe with impressive precision. The current best estimates suggest that the universe is about 13.8 billion years old. It's a remarkable synergy. Stargazing ancient stars, analysing faint afterglows from the dawn of time, and measuring the cosmic expansion, each piece fitting together like a cosmic puzzle. This blend of observations and theories helps scientists piece together the history of everything we see, reaching back through time to answer one of our most fundamental questions: how old is the universe? And it's a reminder of just how limited our perspective may seem, yet how powerful our curiosity and ingenuity are in unraveling its secrets. The observable universe includes everything we can see, from stars and galaxies to cosmic phenomena. That light has had time to reach us since the universe's beginning. However, it's only a part of the entire universe. Its size is limited by two main factors: the age of the universe and the finite speed at which light travels. The universe is about 13.8 billion years old. Light from the farthest objects has been travelling toward us for nearly that long. When we observe a galaxy 20 billion light-years away, we see it as it was 20 billion years ago, looking back into cosmic history. But light from regions farther than our current observable limit hasn't had enough time to arrive, meaning those regions are beyond our reach with current technology and understanding. Light travels at about 300,000 kilometers per second, which is fast but not infinite. No matter how powerful telescopes become, they can't see beyond a certain point because the light from beyond that boundary simply hasn't reached us yet. Our night sky is like a snapshot of the universe's past, constrained by the time light takes to reach us. This boundary is known as the cosmic horizon. It's similar to a horizon on Earth, the place beyond which you cannot see because the land drops away or the curve hides it. The cosmic horizon is not a physical boundary, but a limit imposed by the universe's age and the finite speed of light. As the universe expands, this horizon grows, revealing more of the universe over time. But at any moment, there's a fixed radius beyond which we cannot observe because light from beyond hasn't had enough time to reach us since the universe's inception. The universe is also expanding at an accelerating rate driven by dark energy. This affects the cosmic horizon because space itself stretches, causing distant galaxies to recede faster than light in some cases. Consequently, some galaxies emitting light long ago are now beyond our observational reach. Their light set out bound for us, but due to cosmic expansion, takes longer to arrive. Sometimes galaxies now receding faster than light cannot be observed because their light's journey is stretched and delayed. Essentially, the observable universe is like a slowly illuminated cosmic billboard. Only the light from nearby regions has had time to reach us. Regions beyond the cosmic horizon remain dark and unobservable, possibly existing but forever beyond our reach due to physical limitations. Our understanding is constrained by the speed of light and the universe's age. This realization reminds us of our place in the cosmos. The universe is immense, beyond our imagination. What we see is just a small window into its vastness. As the universe continues to expand, our view gradually uncovers new parts of it, but the full picture remains forever out of reach. Our universe isn't just size, it's intricately mysterious, challenging our understanding of space, time, and reality. The finite speed of light and the universe's age set fundamental limits. The cosmic horizon shifts outward over time, revealing more of the universe's history, yet a boundless universe, or multiverse, could exist beyond it, forever hidden from view. This underscores how much remains unknown, and how our observations are just a glimpse into something far greater and more mysterious than we can currently perceive. Standing on a hilltop at night, gazing up at the stars, every point of light reveals a glimpse into the past, some peering back billions of years. This is because light from distant galaxies takes millions or even billions of years to reach us. The universe is constantly expanding, stretching space-time itself, creating a boundary known as the cosmic horizon. The cosmic horizon is the maximum distance from which light has had enough time to reach us since the universe's beginning about 13.8 billion years ago. It's not a physical barrier, but a limit set by the finite speed of light and the universe's age. Think of it as the universe's viewing window, constraining what we can observe. Since light takes time to travel, the farther we look into space, the further back in time we see. For example, observing a galaxy a billion light-years away means seeing it as it was a billion years ago. The cosmic horizon marks the boundary beyond which light hasn't had enough time to reach us. No matter how powerful our telescopes, we are forever limited by this boundary. This boundary profoundly influences our understanding of the cosmos. It establishes a fundamental limit. We can never know what lies beyond the cosmic horizon. The universe might be infinitely large with regions forever beyond our reach, or finite but unobservable. In either case, the horizon defines the limits of human knowledge. It also tells a story about the universe's history. The observable universe functions like a giant clock, each light year representing a period in the universe's past. The cosmic horizon slices through spacetime, marking the oldest light we can detect, such as the cosmic microwave background, CMB, the faint afterglow of the Big Bang. We see the CMB as originating only 380,000 years after the universe's beginning, when it was still a hot, dense plasma. Everything beyond this boundary remains forever out of view. The cosmic horizon deeply impacts cosmology, the study of the universe's origins, structure, and fate. It raises essential questions. Will the universe continue expanding forever? Could distant regions someday come into view if expansion slows or reverses? Or will they stay forever hidden beyond any observational reach? The answers depend on the universe's expansion rate, influenced by dark energy and other mysterious factors. Understanding the cosmic horizon also helps explain why the universe appears so uniform on large scales. Since observations are limited to within the horizon, the observable universe is a finite patch. This supports models suggesting that rapid inflation in the universe's earliest moments smoothed out initial irregularities within our observable region. In essence, the cosmic horizon acts as a humbling boundary. It reminds us that much of the universe's vastness remains beyond our reach, filled with mysteries we may never see. It prompts us to ponder the nature of reality, the limits of observation, and the universe's incredible expanse. Each discovery beyond our cosmic doorstep broadens our insight, not just into what is out there, but into what it means to be explorers in a universe stretching beyond the limits of our understanding. The cosmic microwave background, or CMB, is a faint glow filling the universe. Imagine standing in a dark room and seeing a soft, uniform light, except this glow is not just illumination. It's a snapshot frozen in time from nearly 400,000 years after the universe was born. This tiny, uniform brightness is a relic from the earliest moments of everything we know, a whisper from the universe's first moments that still lingers today. Before the universe was 400,000 years old, it was a hot, dense soup of particles, protons, neutrons, electrons, cooked together in a fiery state. Light couldn't travel freely because it kept scattering off charged particles, making the universe opaque. As the universe expanded and cooled, electrons combined with protons in a process called recombination, forming neutral atoms. Suddenly, photons, which had been bouncing around endlessly, could travel unimpeded through space. This moment of transparency marked the release of the CMB. It has been traveling ever since, its wavelength stretching as the universe expands. Originally a hot glow, it cooled over the eons into faint microwave signals detectable today. When scientists first observed this microwave glow in the late 1960s, it was a game changer. It provided the universe's first full picture, a baby picture, showing the universe in its earliest observable state. What does the CMB reveal about the early universe? It provides strong evidence for the Big Bang theory. Acting as a cosmic time capsule, it shows conditions just moments after the universe began. Its uniformity indicates a vast, rapidly expanding universe that was nearly the same everywhere in its early stages. Tiny temperature variations, just 1 part in 100,000, are ripples indicating minute density differences. These fluctuations are the seeds from which galaxies, stars, and planets eventually formed. Analyzing these fluctuations allows scientists to reconstruct the universe's history. They measure its expansion rate, the influence of dark matter and dark energy, and refine estimates of its age, about 13.8 billion years. The pattern of temperature differences aligns with predictions from the inflationary model, where the universe underwent a brief, rapid expansion faster than light shortly after the Big Bang. The CMB also offers insight into the universe's composition. Detailed measurements reveal proportions of ordinary matter, dark matter, and dark energy, showing how these components shaped cosmic evolution. Since the radiation originates from a time before stars and galaxies formed, studying it helps us understand physics under conditions impossible to replicate on Earth. Looking into this ancient glow provides a picture of the universe's infancy, a glimpse into its earliest moments. It's like viewing the universe's earliest diary, full of clues, secrets, and stories about how the cosmos came to be in its astonishing, expanding state. The CMB is a vital window into understanding our universe's origin, its evolution, and its fundamental physics, illuminating the story of how everything began and developed into the vast cosmos we observe today. Imagine looking up at the night sky, each star and galaxy a tiny point of light shining across billions of miles. Now picture that space itself isn't static, it's stretching, expanding, evolving. This expansion of space profoundly affects what we observe, shaping our view of the universe in ways that are both mind-boggling and fundamental. When Edwin Hubble first observed that galaxies are moving away from us and that their speed increases with distance, he revealed the universe is expanding. Instead of thinking of galaxies rushing through space, it's space itself that's stretching, carrying galaxies along. Think of dots on a balloon surface. As you inflate the balloon, the dots move away from each other, not because they are moving on their own, but because the surface expands. This helps us understand how the universe operates on grand scales. But this expansion isn't just about galaxies drifting apart. It influences how far we can see and what we understand about the universe's history. Light takes time to travel, so when we observe distant galaxies, we're peering back in time. The farthest objects are glimpses of the universe when it was much younger. Because space expands, these galaxies are speeding away from us, stretching the light that reaches us, shifting it toward the red end of the spectrum. This phenomenon, called redshift, is a key clue that reveals the universe's expansion. Over vast periods, expansion causes some regions of space to become so distant that their light can never reach us. Imagine a galaxy moving away so fast that its light will never arrive here. Parts of the universe slip beyond our observational boundary, forever out of reach. Within this cosmic horizon, the universe appears finite, but from our vantage point it looks as if galaxies continually move farther away, creating an observable universe that's constantly stretching. This stretching space-time also causes the universe's expansion to accelerate. Observations of distant supernovae show that the expansion isn't slowing but speeding up, driven by a mysterious force called dark energy. Dark energy seems to push space apart faster over time. As a result, the observable universe continues to grow, but only up to a point, beyond which the expansion becomes so rapid that galaxies beyond a certain distance are forever out of view. The cosmic microwave background, the faint afterglow of the Big Bang, offers a snapshot of the universe when it was just a few 100,000 years old. Expansion cooled this primordial light from intense heat to the chilly microwave radiation we detect today. It tells a story about the universe's infancy, but because space has been stretching since then, those initial signals are now stretched into long microwave wavelengths, observable over enormous distances. The expansion of space doesn't just make galaxies drift apart, it transforms our entire view of the cosmos. It dictates what we observe, how early in history we can see, and how the vastness continues to evolve. It's like a cosmic canvas, stretching and expanding forever, shaping the very fabric of our universe and revealing the deeper secrets of its origin, growth, and destiny. Observing extremely distant objects such as galaxies, quasars, and supernovae allows us to peer into the universe's infancy, offering insights into how it began, evolved, and the fundamental laws that govern it. Light takes time to reach us, so when we observe a galaxy a billion light years away, we see it as it was a billion years ago, when dinosaurs roamed Earth. This cosmic time machine reveals early universe structures, composition, and the processes that formed the first stars and galaxies. Studying these distant objects provides key insights into the universe's expansion. Redshift, the shift of light toward red wavelengths, helps gauge how fast the universe expanded at different epochs. Since the Big Bang, the universe has been stretching, and measurements of redshift have shown that this expansion is accelerating due to dark energy. Understanding this acceleration helps predict whether the universe will expand forever, slow, or reverse. Distant object observations also illuminate galaxy formation and evolution. By analysing their shapes, sizes, and contents, scientists understand how cosmic structures assembled. Did early galaxies collide? Did some form stars rapidly while others grew slowly? These observations refine models of cosmic evolution, revealing the dynamic processes shaping the universe into its present form. Supernovae, the explosive deaths of stars, serve as cosmic markers. Their brightness measurements allow astronomers to determine distances precisely through standard candle methods. This technique was pivotal in discovering the universe's accelerating expansion. Supernovae disperse heavy elements like carbon, oxygen, and iron, building blocks for planets and life. Observing distant supernovae helps reveal how the universe became enriched with these elements. Quasars, luminous centers of distant galaxies powered by supermassive black holes, provide critical info on black hole growth and galaxy formation. They are visible across vast distances, acting as cosmic beacons that illuminate the early universe. Studying quasar properties helps us understand how supermassive black holes assembled quickly within the first billion years after the Big Bang. Every observation of these objects tells a story about the universe's past. As telescopes and detection methods improve, we will uncover more about this ancient universe, its origins, evolution, and destiny. Looking into space is not just about seeing faraway objects, it's about understanding our origins, how the cosmos formed, and its possible future. These observations reveal the universe's history and the processes that shaped it, helping us understand our place within it. Advances in telescope technology promise to unlock further mysteries, revealing new details about early cosmic epochs and ongoing expansion. From faint supernovae to energetic quasars, each discovery enhances our comprehension of cosmic history and fundamental physics. Examining the universe's most distant and ancient stages enables scientists to piece together the story of everything, its beginnings, evolution, and potential future. This pursuit satisfies curiosity and deepens our understanding of reality's fundamental nature, shedding light on matter, energy, and space-time origins. With every new discovery, we approach a clearer understanding of our cosmic roots, revealing how the distant past holds answers to questions about existence, formation, and the universe's ultimate fate. When we look at distant galaxies, we're essentially peering back in time. Light from these far-off worlds takes millions or even billions of years to reach us. By the time this light arrives, the galaxy that emitted it may have changed dramatically or no longer exist. This cosmic time travel allows us to uncover the universe's history, studying how it evolved over billions of years. For example, observing a galaxy 10 billion light-years away means we see it as it was 10 billion years ago, an entirely different universe, likely filled with young stars and emerging planetary systems. The farther away the galaxy, the further back in time we are looking. Studying these ancient light signatures helps astronomers build a timeline of cosmic development, revealing how galaxies form, evolve, and sometimes fade. One major insight from distant galaxies is understanding the universe's expansion. When Edwin Hubble observed that galaxies are moving away from us faster as their distance increases, he revealed that the universe is expanding. The farther a galaxy is, the faster it appears to recede. By examining galaxies at different distances, scientists can trace how the universe expanded over time. This discovery led to the concept of dark energy, an unknown force driving the acceleration of this expansion. Looking deeper into space also reveals conditions of the early universe. The cosmic microwave background radiation is a faint glow left over from the Big Bang. When scientists observe distant galaxies, they're effectively looking back to when the universe was a few 100 million years old. The properties of these early galaxies, such as stellar types, chemical makeup, and structure, give clues about the formation of the first stars and galaxies from primordial gas. These observations tell the story of the universe's infancy, showing how matter clumped under gravity to create the large-scale structure we see today. Distant galaxies also act as natural laboratories for extreme phenomena that occur rarely or under extraordinary conditions. Some exhibit intense starbursts, illuminating how stars ignited in the universe's early days. Others host supermassive black holes that influence their entire host galaxies, helping researchers understand how these giants grow and shape their surroundings. In essence, observing distant galaxies is more than capturing pretty pictures. It's a way to read the universe's history book. Each galaxy presents a chapter written billions of years ago, revealing how everything, from tiny planets to vast galaxy clusters, came into being. Data gathered from various distances and epochs allows astronomers to piece together a cohesive story of cosmic evolution, continuously refining our understanding. The most surreal aspect is realizing that when we observe the universe through light years, we are witnessing its past in vivid detail. Time becomes a canvas of light that has traveled unimaginable distances, painting pictures of the universe's history. Every distant galaxy is a time capsule, a message from the deep past, telling us how everything began, grew, and continues to evolve in this vast expanding cosmos. Imagine staring into the night sky and realizing that some objects twinkling back at us are so distant that their light has traveled for billions of years just to reach us. These cosmic beacons challenge our understanding, pushing the boundaries of what we can comprehend about scale and time. The most distant objects visible from Earth give us a glimpse into the universe's infancy, allowing us to witness conditions when the universe was a fraction of its current age. For example, some of the most distant galaxies discovered are over 13 billion light-years away. When we say a galaxy is 13 billion light-years distant, we mean its light left it 13 billion years ago. Since the universe is about 13.8 billion years old, we're observing galaxies as they existed shortly after the Big Bang, roughly a billion years after its inception. These ancient galaxies are remote relics, holding clues to early cosmic evolution. Their light has travelled through vast cosmic voids, overcoming expansion, yet still reaches our telescopes, whispering stories from the universe's early days. What about quasars? These luminous, active, supermassive black holes at the centres of young galaxies outshine entire galaxy clusters. Some quasars are over 13 billion light-years away. Their extreme brightness enables us to detect them across enormous distances, helping us understand how supermassive black holes formed and grew during the universe's infancy. Observing these objects provides insights into conditions less than a billion years after the Big Bang. Even more astonishing are gamma-ray bursts, the brightest electromagnetic events since the Big Bang. Some originate over 12 billion light-years away. These intense flashes mark the deaths of massive stars or neutron star collisions, functioning as cosmic lighthouses. Their light travels across vast space, carrying information about the universe's early chemical composition and star formation rates. These brief yet powerful bursts help reveal the universe's formative epochs. Another key cosmic signal is the cosmic microwave background radiation, the faint glow permeating the universe. This radiation is a relic from about 370,000 years after the Big Bang and arrives from a distance of roughly 13.8 billion light-years. Observing this ancient light is like viewing a photograph of the universe's first moments. It reveals a hot, dense plasma that cooled and expanded into the universe we see today. Each of these distant objects, galaxies, quasars, gamma-ray bursts, serves as a cosmic lighthouse, illuminating the universe's earliest epochs and the vastness beyond human comprehension. They function as time capsules, offering glimpses into eras long before humans existed, challenging us to grasp the scale of the cosmos. The fact that we can detect light travelling across billions of light-years opens an extraordinary window to understand the universe's history and evolution. In sum, these distant objects reveal key insights about the universe's origin, growth, and the physical laws that govern it. From galaxies that date back to mere billions of years after the Big Bang to the faint glow of cosmic microwave background radiation, they lend us a front-row seat to cosmic history. Their light, travelling across enormous distances, continues to reach us, allowing us to piece together the story of everything we see and everything we are. Imagine peering into the night sky, where distant galaxies and stars stretch across space. A key phenomenon affecting what we observe is cosmic redshift, which reveals the universe's expansion and helps measure cosmic distances. Cosmic redshift occurs because the universe itself is stretching over time. Picture space as a stretchy fabric. As galaxies move away from us, the light they emit travels through this expanding medium. This stretching elongates the light waves, shifting them toward the red end of the spectrum. This red shift isn't just a colour change. It's a direct indicator of how fast an object is receding from us. When a galaxy emits light, that light begins its journey to Earth. If the galaxy is far enough, the expansion of space between us and it causes the light to stretch as it travels. By the time it reaches our telescopes, its wavelength is longer than when emitted. This phenomenon is called redshift. The degree of redshift indicates the speed at which the galaxy is moving away. The more stretched the light, the faster the galaxy recedes. In cosmology, redshift acts as a cosmic speed indicator. For nearby galaxies, redshift correlates with velocity, consistent with Hubble's law, which states that a galaxy's recessional speed increases with distance. This relationship has profoundly shaped our understanding of an expanding universe, transforming observations into insights about cosmic history. As light from more distant sources reaches us, its redshift becomes even more pronounced. For galaxies billions of light years away, their light is shifted into infrared or radio wavelengths beyond visible spectrum. Such a deep red shift signals that these galaxies are both far away and that their light comes from an earlier universe epoch when galaxies were closer and the cosmos younger. Remarkably, cosmic redshift not only indicates distance, but also provides a window into the universe's expansion timeline. By measuring how much the light has been stretched, scientists estimate the light's travel time and thus infer the universe's age. This relationship has led to critical discoveries, including the realization that the universe's expansion is accelerating, driven by dark energy. However, cosmic redshift complicates our perception. The farther an object is, the more its original light has been altered by expansion. The colours and wavelengths we observe are shaped by the universe's stretching, not just by the source itself. Astronomers must account for redshift carefully to understand the true properties of distant objects like galaxies, stars, or supernovae. Cosmic redshift is more than a passive effect. It acts as a storyteller, revealing the universe's past, its growth, and the forces, like dark energy, that influence its evolution. It reminds us that the universe is dynamic, constantly expanding and stretching the fabric of space and time. This ongoing expansion challenges previous notions of a fixed universe, deepening our understanding of its history and future. In essence, cosmic redshift unlocks the story of the universe's evolution. It shows us that the cosmos isn't static, but a vast, changing entity. As light travels across this expanding landscape, it carries the tale of a universe that has been growing for billions of years, providing essential clues about its origins, its expansion, and the mysterious forces shaping its destiny. Peering back billions of years to glimpse the universe's earliest moments is like trying to look through a foggy window into a distant past shrouded in layers of cosmic history. One of the biggest hurdles is that the universe was essentially opaque in its first few 100,000 years. Imagine a newborn universe wrapped in a dense, hot soup of particles, protons, neutrons, electrons, that constantly scatter photons. Light couldn't travel freely during this time, making it impossible to observe these earliest moments directly. Only after the universe cooled enough for protons and electrons to combine into neutral atoms, recombination, could photons travel unimpeded, forming what we now detect as the cosmic microwave background radiation. Even then, capturing the universe's infancy isn't simple. The signals from these early moments are incredibly faint and often drowned out by cosmic noise or foreground emissions from our galaxy. Extracting the subtle fingerprints of processes that happened over 13 billion years ago requires extremely sensitive instruments and sophisticated data analysis. Instruments like the Planck satellite have provided invaluable data on the cosmic microwave background, but they are still limited, unable to produce detailed images of the first moments, only broad patterns in temperature fluctuations. The vast distances involved mean that the light from those epochs has been stretched, redshifted, by the universe's expansion. This shift moves the emitted light into longer wavelengths, often microwave or radio. Observing these signals demands specialized detectors capable of picking up faint redshifted photons amid foreground noise. From an engineering perspective, this makes observations challenging, requiring advanced technology and precise calibration. Another limitation stems from the fundamental physics involved. At scales smaller than the Planck length, or energies higher than the Planck energy, conditions believed to have existed during the first fractions of a second, the laws of physics as we understand them break down. Quantum gravity, string theory, and other models aim to describe these realms but lack experimental confirmation. Without direct data, understanding what occurred during these initial instants remains speculative, yet these moments could hold the key to understanding the universe's origin. Our cosmological models, though remarkably precise, depend heavily on assumptions and interpretations that can limit accuracy. Uncertainties in dark matter, dark energy, and other parameters mean our reconstructions of early universe conditions are only as solid as these models are reliable. Because the initial conditions are so far removed in time and physical state, piecing together an exact picture involves extrapolation and inference, both inherently uncertain. Studying these earliest moments is more about decoding faint whispers carried across eons, signals that have been stretched, obscured, or transformed by cosmic evolution. Until future technologies can pierce deeper or interpret signals more accurately, our understanding remains a blend of science, imagination, and inference. This pursuit highlights the universe's humbling complexity and its capacity to inspire awe. To grasp the enormous scales of the universe, humans have developed a fascinating array of mental tools, imagery, and scientific measures that help us make sense of something so vast it defies everyday experience. At the heart of this effort is the idea that while our minds are limited in scale, the universe itself operates on dimensions that stretch beyond intuitive understanding, so we create ways to bridge that gap. One of the most powerful tools we've used is the concept of light years. A light year is the distance that light travels in 1 year, which is roughly 6 trillion miles or 9 trillion kilometers. This unit allows us to tell stories about objects billions of light years away without constantly referencing mind-boggling numbers. Instead, we think in terms of how many years light takes to reach us, turning cosmic distances into a kind of cosmic clock that's easier for us to comprehend. Imagine looking up at the night sky. Some stars are a few light years away, while others are thousands or even millions of light years distant. When we see those stars, we're actually looking back in time, seeing the light they emitted years or even millions of years ago. This idea that the light we observe has travelled across the cosmos for eons turns the universe into a giant time-travelling archive. It's as if every night sky is a historical record, allowing us to glimpse into the universe's past just by peering upward. Scientists also use visual metaphors to make sense of scale. They might compare galaxies to grains of sand scattered across entire beaches, or stars to tiny specks of dust visible only with powerful telescopes. These images, while still simplifications, give us a mental picture of how unimaginably dispersed and vast the cosmos truly is. It's like trying to conceive of a network that connects all the dots, each dot being a galaxy or star system, separated by distances so vast that light takes millions of years to traverse between them. Another way we cultivate understanding is through the use of scale models and computer simulations. Imagine a giant map that condenses the entire universe into a manageable size, with distances scaled down so that we can explore the relationships between objects while still appreciating their true proportions. These models aren't just educational, they're vital for visualizing cosmic phenomena like the expansion of the universe or the formation of structures over billions of years. Humans also tend to put cosmic scales into context by comparing them with familiar objects. For example, if the sun were the size of a grapefruit, Earth would be a tiny bead just 30 feet away, and the nearest star would be a sphere several miles away. These analogies help our minds jump from intuitive, everyday experiences to the mind-expanding vastness of space. All of these strategies, units like light years, visual metaphors, models, and relatable comparisons, serve as mental bridges. They enable us to conceptualize and grapple with the universe's seemingly infinite scales without losing our footing. It's a testament to our curiosity and creativity that, even with the universe's enormity, we can develop mental frameworks that bring these cosmic distances into focus, one light year at a time. Imagine trying to picture a distance so vast that even travelling at the speed of light, it would take years, centuries, or billions of years to cross. Our everyday experiences are rooted in distances we can easily understand, walking across a room, driving down a street, or flying across a continent. When we look into the night sky, those familiar rules break down. The distances between stars, galaxies, and the universe itself stretch beyond our natural intuition. One reason it's difficult to grasp these cosmic distances is that they're outside the range of our everyday experiences. Our brains evolved to navigate manageable distances. Think of the length of a few football fields or the miles between cities. Our senses are tuned for these ranges, where motion is quick and sizes are easy to visualize. But the universe operates on scales so enormous that imagining millions or billions of light years defies our innate sense of scale. A light year, the distance light travels in a year, roughly 6 trillion miles, illustrates this. Even at the speed of light, it would take a year to reach just one nearby star. Our minds struggle to internalize what 6 trillion miles truly means. It's not just a big number. It's almost impossible to fathom because it exceeds any physical or experiential reference point we have. Another challenge is the relativity of perception. We're used to seeing objects move and distances change over human timescales. In the cosmos, events billions of years old are only now reaching us. The universe is constantly expanding, stretching space itself. When we observe a galaxy a billion light years away, we're seeing it as it was billions of years ago, peering into the universe's past. This concept is mind-bending. We're not just looking at distant objects, but at the history of the universe itself. Time also distorts our understanding. In daily life, time is linear and predictable, but cosmic distances stretch that concept. A galaxy millions of light years away experienced events long before humans walked Earth. Yet, because their light takes so long to arrive, we're only now observing those events. Space and time are woven into a four-dimensional fabric that challenges our straightforward notions of cause and effect. The universe's immense scale can also make us feel insignificant. For instance, the Andromeda Galaxy, about 2.5 million light years away, feels both mind-boggling and disorienting. It makes our ideas of travel, communication, and existence seem trivial. Yet, paradoxically, these distances give us a window into the cosmos that existed billions of years ago, connecting us to the universe's history. These factors, our experiential limitations, the nature of light and time, the universe's expansion, all create an almost insurmountable mental hurdle. Our brains were never designed to grasp such scale, which explains why cosmic distances evoke awe, wonder, and incomprehension. Instead of understanding these distances straightforwardly, we rely on numbers, physics, and mathematics to bridge the gap, accepting that some aspects of the universe will forever challenge our innate intuition. Imagine trying to grasp the vastness of the universe, not with a tape measure or a ruler, but with your mind stretched across unimaginable distances. It's here that imagination becomes an essential tool, acting as our bridge to comprehend scales that defy everyday experience. When we talk about objects billions, even trillions, of miles away, the mind struggles to picture such distances. Our brains are wired to understand size and space in familiar terms, but the universe doesn't operate on the same scale. That's when imagination steps in, transforming abstract numbers into mental images that help us process what those enormous distances truly mean. Take the concept of a light year. It's a distance, about 6 trillion miles, that light travels in a year. To understand it, the mind might imagine a ray of light zipping through space, covering a mile in just a tiny fraction of a second. Yet, when we talk about a galaxy that's billions of light years away, we're saying that the light we see today left that galaxy billions of years ago. The entire universe during that time was vastly different, and that realization requires us to stretch our imagination further, to picture not just distances but the passage of cosmic time, intertwined with the universe's history itself. Imagination helps us convert these sweeping numbers into stories. We imagine light as a messenger traveling across eons, carrying images of galaxies as they once were. This mental exercise turns a number into a narrative, an ancient photograph emerging from the darkness. Without imagination, these concepts remain cold figures, disconnected from our human experience. But with imagination, we see beyond the numbers, visualizing the journey of photons across the expanding cosmos and how distant objects are snapshots frozen in time. Furthermore, imagination enables us to conceptualize cosmic phenomena linked to these scales. Redshift, for example, shifts the light from galaxies towards the red part of the spectrum, indicating their recessional velocity and their distance from us. To grasp this idea, we must picture space itself stretching, like a rubber sheet being pulled apart, and light waves lengthening as they traverse growing distances. Visualizing this cosmic stretching transforms complex physics into an accessible story, deepening our understanding of how the universe evolves over billions of years. Our imagination also shapes the very questions we ask. When pondering if life exists on planets billions of miles away, or how stellar events from long ago influence our present universe, we must expand our mental horizons. These questions aren't just about numbers, they're about understanding a universe that is interconnected across time and space in ways we can't directly see or experience. Our imagination allows us to connect the dots, to envisage the conditions billions of years ago that led to stars, planets, and perhaps life itself. In the end, imagination doesn't just help us comprehend the universe's scale, it transforms the cold, vast distances into stories we can relate to. It lets us bridge the infinite gap between head and cosmos, making the unfathomable fathomable. As we gaze into the night sky, It's our imagination that enables us to see the universe not as a distant, unknowable expanse, but as a cosmic story unfolding across distances that break our minds into awe and wonder. Imagine trying to grasp the vastness of the universe with only numbers and equations. Daunting, isn't it? That's where visualizations and models become our cosmic bridge. They transform the abstract, the intangible, into something our minds can hold on to. Picture a simple diagram of the Milky Way. It's not just a swirl of stars, but a tangible map that hints at the scale and structure of our galaxy, allowing us to see how stars are distributed, how regions of dense star formation fit into the grand pattern. These visual tools ground the staggering distances into familiar concepts, helping us see that a star a few light years away is like a neighbour in cosmic terms, while others, thousands or millions of light years distant, stretch our understanding of size. Models like the expanding universe simulations come into play here too. They don't just show us static pictures, they animate the past, present and future of cosmic evolution. Think of a simulated universe gradually expanding over billions of years. It's a story told visually, revealing how galaxies drift apart and how light from distant objects has been stretched and shifted by that expansion. By watching these models, scientists and curious minds alike can better grasp phenomena like redshift, which strings galaxies away from us and indicates the universe's relentless growth. Seeing this play out helps us understand that the universe isn't static. It's a living, expanding entity, and the distances we observe are products of this cosmic dance. Furthermore, visualizations of light paths deepen our comprehension. When astronomers visualize the journey of light through space, from a distant galaxy to our telescopes, it's as if we're tracing the universe's history. These diagrams often show how light from the most distant objects has travelled for billions of years, giving us a window into the universe's infancy. They show us that when we look at a galaxy a billion light years away, we're peering back in time, seeing the universe as it was when it was much younger. This isn't just a neat trick, it's a fundamental tool for understanding the universe's timeline. Models also help us visualize cosmic distances through scale comparisons. For instance, by using scaled-down models, scientists might show that if the Sun were the size of a grapefruit, Earth would be about 35 meters away, and the nearest star would be hundreds of thousands of kilometers distant. These mental images make the incomprehensible sizes and gaps more approachable. They bridge the gap between abstract numbers, like millions or billions of light years, and something tangible that we can relate to. In essence, visualizations and models act as cosmic storytellers. They turn raw data into compelling narratives, stories that allow us to perceive the vastness of the universe not just as an incredible number, but as a series of interconnected, understandable images. They remind us that behind every distant light, there's a story of time, space, and profound scale, waiting to be uncovered. By making the universe's scale more accessible, these tools ignite curiosity, helping us realize that even the most distant and ancient light has a story to tell about the universe's grand journey. Contemplating the universe's immense size pushes our minds to the limits of understanding. Measuring distances in light years or parsecs is one thing. Grasping their true meaning for our place in the cosmos is another. The universe's vastness stretches our notions of scale, time, and reality itself. As we gaze into space, we see not just distant galaxies, but also look into the past, viewing objects as they were billions of years ago. This raises profound questions about existence, time, and our understanding of reality. One key implication concerns observation and knowledge. Light takes billions of years to travel across space, so when we observe a galaxy a billion light years away, we see it as it was then, not now. Our knowledge is limited to the universe's past, suggesting that our perception of reality is inherently constrained by the speed of light, a universal speed limit. This means that the universe keeps its current state just beyond our reach, hiding its true nature behind a distant light horizon. The universe's size also prompts us to question human significance and existence. With billions of galaxies, stars, and potentially countless planets, the universe appears vastly more populated and complex than we imagined. This scale challenges our sense of importance. We are tiny specks within an immense cosmos. Yet it also fills us with awe, prompting reflection that we are part of a vast unfolding story rather than its center. Furthermore, contemplating the universe's size leads to questions about time and destiny. The universe began around 13 billion years ago with the Big Bang. Since light from distant galaxies takes billions of years to reach us, what we see is effectively ancient history. Can we ever understand the universe's current condition, or are we forever limited to glimpses of its past? This uncertainty invites existential reflection. Living in a universe that is expanding, aging, and revealing only fragments of its story raises questions about ultimate truths potentially beyond our grasp, hidden behind the expanses of space and time. On a philosophical level, the universe's enormity fosters humility. It reminds us how small we are amid seemingly infinite nothingness. Paradoxically, it can also invoke a sense of connection. Knowing that light from distant stars travelled unfathomable distances to reach us creates a silent, profound link to the cosmos's history. We are connected to the universe in ways both deep and subtle. The vastness also prompts questions about the nature of existence itself. Are the universe and all others part of an infinite cycle, or is our cosmos isolated? If infinite, every conceivable scenario could happen somewhere else, every possibility played out. If finite, questions arise about its ultimate fate, heat death, rebirth, or something else. These questions straddle science and philosophy, urging us to think beyond immediate experience, beyond the limits of light and time, into realms of infinite possibilities and the meaning of reality. The universe's staggering scale isn't just a scientific marvel, it invites us to ponder fundamental questions about ourselves, existence, purpose, and the nature of reality. It calls us to embrace wonder, humility, and curiosity as we venture deeper into the cosmic night, realizing that the vastness of space is also a mirror reflecting our deepest philosophical inquiries. The idea of multiverses, multiple or even an infinite number of universes beyond our own, may sound like science fiction, but some of the most intriguing and groundbreaking theories in physics and cosmology suggest that our universe might just be one bubble in an enormous cosmic foam. These theories attempt to explain the bizarre, often mind-boggling properties of our universe and the surprising fine-tuning of its physical laws. One of the earliest and most influential concepts comes from the theory of cosmic inflation, proposed by Alan Guth in the early 1980s. Inflation suggests that, in the moments immediately following the Big Bang, our universe underwent a rapid and exponential expansion. But what if this inflation didn't just happen once? Instead, some physicists believe that inflation might be a continuous process, happening in different regions of space, kind of like a churned-up ocean of bubbles. Each of these bubbles could then become a universe with its own set of physical laws and constants. This idea, called the multiverse from inflationary cosmology, suggests that our universe is just one of countless others, each born from quantum fluctuations during the inflationary process. Another compelling framework comes from string theory, which posits that the fundamental building blocks of reality aren't point particles, but tiny, vibrating strings. String theory requires extra dimensions, beyond the familiar 3 dimensions of space and 1 of time, that are compactified or curled up at incredibly small scales. Some versions of string theory propose a vast landscape of possible solutions, each corresponding to different ways these extra dimensions can be shaped and sized. The result? A multiverse consisting of a multitude of universes, each with its own unique set of physical laws, cosmological constants, and particle properties. This so-called string landscape might explain why our universe has the particular characteristics it does, because in a vast multiversal ensemble, almost any combination of laws is possible. Then there's the concept of the many worlds interpretation of quantum mechanics, proposed by Hugh Everett in the 1950s. While traditionally seen as a way to interpret quantum phenomena without collapse of the wave function, it also hints at a kind of multiverse. According to this view, every possible outcome of a quantum event actually occurs, but each one in a separate branching universe. When a quantum measurement is made, the universe splits, one universe for each outcome. Over cosmic timescales, this branching results in an unfathomably vast multiverse, each universe with its own history, galaxy arrangements, and perhaps even different versions of physical laws. Some physicists also entertain the idea of a multiverse stemming from the very nature of the multiverse itself, an infinite cosmos that simply exists in a state of never-ending random fluctuations. In this picture, different regions can spontaneously nucleate and evolve into universes, each with different properties and histories. While none of these theories have been conclusively proven, many remain speculative and are difficult to test. They each offer fascinating possibilities. They challenge our notions of reality and stretch our understanding of space and time. They suggest that what we see, measure, and experience might just be a tiny fragment of an unimaginably vast and varied cosmos, where the only limit is the very nature of our imagination and the laws of physics themselves. The idea of multiple universes, or the multiverse concept, challenges traditional cosmology by expanding our cosmic horizon beyond a single universe. For centuries, scientists envisioned one universe with a beginning, perhaps a Big Bang, and an eventual fate. Traditional cosmology assumes our universe is unique and governed by predictable physical laws. Observations, such as galaxies and cosmic microwave background radiation, tell a consistent story explained through relativity and quantum physics, allowing us to trace its history and predict its future. But what if our universe isn't alone? What if countless others exist, each with its own physical laws, some similar, others quite different? Multiple universes complicate the principle of testability fundamental to science. Observation, experimentation, and falsifiability are essential, but how do we observe something potentially forever beyond our reach? Some multiverse theories arise from inflationary cosmology, where rapid expansion after the Big Bang could have created many pocket universes, each with distinct parameters. These universes could be causally disconnected, separated by boundaries impossible to cross, making direct observation impossible. This raises profound questions. Can something be considered scientific if it can't be observed or verified? Many scientists find the multiverse compelling because it could explain why our universe's physical laws and constants are fine-tuned for life. Perhaps our universe is just one of many, with its specific physics determined by a cosmic lottery, potentially accounting for the constants that allow life to exist. Embracing multiple universes also changes our view of cosmic origins. Instead of a single beginning, the multiverse suggests countless origins, each universe emerging from its own nascent phase. It spurs debates about whether these universes had causes or are the result of quantum fluctuations. Some propose that the multiverse forms a cosmic ensemble, where fine-tuning is less mysterious. Our universe's suitability for life might simply be due to chance within a vast collection of realities. Critics argue multiverse theories risk becoming philosophical speculation rather than empirical science. However, proponents see them as necessary extensions of modern physics, possibly offering insights into phenomena we cannot directly measure. If true, the multiverse could reshape our understanding of reality, prompting us to see our universe as only a small bubble in a vast cosmic ocean. Ultimately, the multiverse concept underscores the limitations of our perspective. It encourages us to think bigger. Imagine our universe as just a tiny fragment within something incomprehensibly larger. Light years become not only distances within our cosmos, but symbols of how much remains unexplored. The universe might be far larger than we can currently grasp, with many more mysteries waiting to be discovered. This idea pushes the boundaries of what we believe possible, urging us to expand our understanding of everything we think we know. The idea that light from other universes might be observable sparks imagination and challenges our understanding of reality. But let's examine what that really means and whether such a concept aligns with current science. Our universe is defined by the cosmic horizon, the furthest distance from which light has had time to reach us since the Big Bang. Light travels at about 209 Nephosin 792 kWs, and since the universe is roughly 13. 8 billion years old, the observable universe extends about 44 billion light-years in all directions. Beyond this horizon, the universe still exists, but the light from those regions hasn't yet reached us, so we cannot observe it directly. What about other universes? In cosmology and theoretical physics, the multiverse, an ensemble of multiple, possibly infinite universes, has gained popularity, especially in inflationary models and string theory landscapes. But these universes are thought to be separated from our own, in ways that seem beyond our reach. Each universe in the multiverse is believed to be causally disconnected, meaning nothing, including light, can travel from one to another. Observing light from a different universe appears impossible with current understanding. Light relies on space-time, something that, in other universes, might not even exist in a form allowing interaction or communication. Even if another universe exists nearby or interacts with ours, the challenge remains. The light from those universes would be travelling through their own space-time separate from ours. Because space-time defines a universe, the idea of light crossing into another universe faces profound theoretical issues. Would such light even exist? Would the laws of physics permit it? Would fundamental constants, like the speed of light, be the same across universes? These questions are currently unanswerable since we lack empirical evidence. Some speculative theories propose that if there were any interaction or leakage of energy or information from other universes, it might appear as subtle anomalies or faint signals in our cosmic background. For example, patterns in the cosmic microwave background, CMB, the afterglow of the Big Bang, have been hypothesized to hint at phenomena beyond our universe. But these ideas are controversial and far from confirmed. They're more like tantalizing clues, suggesting that someday we might find indirect evidence of something beyond our universe. In summary, with our current understanding and the boundaries of our observable universe, it seems highly unlikely that light from other universes is observable. The constraints of causality, the nature of space-time, and the absence of definitive signatures make such observation more science fiction than science. Until physics advances in ways we can't currently imagine, other universes, and any light they might emit, remain beyond our observational reach. They are futures that push us to explore further, but for now, the cosmic curtain remains firmly closed. The idea of a multiverse might sound like science fiction, but intriguing evidence has begun to surface that keeps this concept a real scientific discussion. It's a mind-bender. Imagine our universe, with its billions of galaxies, stars, planets, and the fabric of space-time, as just one bubble among countless others. These other universes could differ wildly, with different physics, constants, or even dimensions. One key piece of evidence comes from the cosmic microwave background, CMB, the faint glow left over from the Big Bang. When scientists examine this relic radiation, they notice tiny irregularities that could be signatures of interactions with other bubble universes, or the remnants of collisions in the distant past. These patterns, akin to ripples on a pond caused by a pebble, might indicate other universes bumping into ours, leaving faint, measurable imprints. While not definitive proof, they are tantalizing hints that our universe could have more neighbors than previously imagined. Another evidence line arises from cosmic inflation theory, which proposes that shortly after the Big Bang, the universe expanded exponentially faster than the speed of light. Some models suggest this rapid expansion was not a one-time event, but could continue in different regions, creating a multiverse of bubble universes. These bubbles might be separate, with different physics and possibly different dimensions or constants. Although we cannot observe these other bubbles directly, the mathematical models supporting inflation make their existence a natural consequence, lending credibility to the multiverse hypothesis. Quantum fluctuations in the early universe also support this idea. Rooted in quantum mechanics, tiny random energy fluctuations might have caused different regions of space to evolve into separate universes. Each could develop differently, leading to a multiverse where physical laws vary from one universe to another. While beyond our cosmic horizon, the occurrence of these well-established quantum fluctuations strengthens the plausibility that multiple universes could arise from similar processes. Some scientists argue that the very constants we measure, such as the strength of gravity or the electron's charge, could vary across different universes. Our universe's finely tuned parameters seem suitable for life, prompting the suggestion that this fine-tuning results from a vast multiverse hosting all possible combinations of constants. In this scenario, it's not surprising we find ourselves in a universe conducive to life, like winning a cosmic lottery, with many universes offering different conditions. Though none of these lines of evidence definitively prove the multiverse's existence, together they create a compelling puzzle. They challenge our understanding of reality, questioning whether our universe is unique or just a slice of a cosmic onion with endless layers. Each discovery pushes the boundaries of science, transforming what was once purely speculative into a frontier rooted in theories and observations. Perhaps someday we will have clearer evidence, proof that beyond our universe lies an infinite expanse of worlds, each with its own story waiting to be uncovered. Imagine a universe where our familiar laws of physics, constants, and even the fabric of space and time are just one of countless others, each with its own set of rules, history, and story. This is the idea of multiverses, a concept that expands our understanding of reality. Its implications are profound, challenging our perceptions of the universe and our place within it. First, consider what a multiverse means for the uniqueness of our universe. For centuries, humans looked up at the night sky, believing our universe was all there was, an entire stage of existence. But with multiverses, that vast stage multiplies exponentially. Instead of one universe, there could be infinite ones, each with different physical laws, constants, and histories. Some might resemble ours, with planets and life, while others could be radically different, beyond our comprehension. This concept forces us to rethink cosmic and realize our universe may be just a small chapter in an immense multiverse story. Another major implication relates to the fine-tuning problem. Our universe's constants seem perfectly calibrated for stars, planets, and life, like the strength of gravity or the electron charge, set so precisely that even tiny changes could eliminate life as we know it. If many universes exist, each with different constants, then our universe's life-permitting conditions might be one fortunate outcome among many. This suggests that what appears fine-tuned may be chance, a cosmic lottery where all possible configurations occur somewhere in the multiverse. It reframes our universe not as an extraordinary coincidence, but as one expected outcome within a broader multiversal landscape. Furthermore, the multiverse raises questions about the nature of reality and causality. If other universes exist beyond our observable horizon, events that seem unlikely or inexplicable locally might be normal elsewhere. Each universe could have its own laws, making a single, unified theory less plausible. Our universe might be just one patch in a vast, diverse multiversal fabric, collectively defying a neat explanation. This shifts the idea that everything can be explained by a single set of laws and suggests reality may be much more complex. This concept also affects science's role of observation and evidence. How can we prove other universes exist? Some propose that effects like cosmic microwave background imprints from universe collisions could offer clues. Yet, for now, the multiverse remains a compelling hypothesis rather than an established fact. This raises questions about the scientific method. Does the inability to directly observe other universes diminish its scientific status, or does it push science toward new territories where philosophy and cosmology intersect? Ultimately, contemplating multiverses expands our view of reality as far more vast and strange than imagined. It invites us to see ourselves not as the center of a single cosmic story, but as part of a grand multiversal saga, where reality is more wondrous and mysterious than ever. Despite remarkable progress in observational astronomy, we face significant technological limits when observing distant light sources. These boundaries influence how much of the universe we can explore and how deeply we can understand the cosmic story told through photons traveling across unfathomable distances. One major barrier is the sensitivity of our telescopes. Light from the most distant galaxies or earlier stars is extremely faint, dispersed over billions of years. Detecting such signals requires instruments capable of capturing tiny amounts of light. Currently, even the most advanced telescopes have thresholds. They can only detect sources above a certain brightness, so dimmer, more ancient objects often remain unseen. Expanding this capacity demands larger mirrors and more sensitive detectors, but constructing large, precise optics is increasingly challenging and costly. The size of telescopes limits their light-collecting ability. Larger collection areas gather more photons, enhancing views of faint objects. Another limitation comes from Earth's atmosphere, which causes atmospheric turbulence, or seeing, blurring incoming light and reducing image sharpness. Adaptive optics systems help by adjusting optics in real time to minimize distortion, but can't eliminate the problem entirely. Space-based observatories avoid atmospheric interference altogether, providing clearer images. However, launching and maintaining these satellites involve logistical challenges, high costs, and limited operational lifespans. Wavelength coverage also constrains observations. Some cosmic phenomena emit primarily in wavelengths absorbed or scattered by Earth's atmosphere, such as ultraviolet and certain infrared light. Space-based instruments are necessary to observe these wavelengths, Telescopes like Hubble and James Webb have broadened our capacity, but each new wavelength window demands specialized, complex and expensive technologies, including advanced detectors, cooling systems, and mirrors. Even with powerful instruments, our ability to analyze signals is limited by noise, cosmic background radiation, zodiacal light from interplanetary dust, and instrumental noise obscure faint signals. Improving sensitivity involves developing better, less noisy detectors. Yet, fundamental limits like quantum noise place hard boundaries on how faint a signal we can detect reliably. Temporal factors also limit observations. The universe is dynamic. Phenomena like supernovae or gamma-ray bursts change or fade over time. To capture transient events, telescopes need rapid response capabilities and continuous monitoring. Scheduling observations and maintaining constant vigilance is challenging, especially for satellites with limited fields of view and operational lifespans, constraining our ability to monitor the cosmos consistently. The universe's vast scale imposes further limits. Some regions are forever beyond our reach. As the universe expands, some galaxies are receding faster than the speed of light relative to us, slipping beyond our observational horizon. Although nothing travels faster than light locally, the expansion means parts of the universe will always remain out of view, regardless of technological advancements. All these limits highlight that our quest to understand the universe continuously pushes against the boundaries of technology. Each breakthrough brings new insights, but the universe's vastness and complexity challenge our ingenuity and resourcefulness. Our pursuit remains an ongoing dance at the edge of possibility, inspiring continued innovation to glimpse deeper into the cosmos. Telescopes and detectors are the eyes that allow us to glimpse the vast, mysterious universe beyond our tiny planet. Without these incredible tools, the universe would remain an elusive, incomprehensible expanse. They serve as extended senses, amplifying our natural capabilities and opening windows into realms far beyond normal human perception. Telescopes function much like giant, superpowered eyes, gathering and focusing light from distant objects across the electromagnetic spectrum. Optical telescopes collect visible light from stars, galaxies, and nebulae, sharpening images and revealing details long hidden from the naked eye. They allow us to see more clearly, magnifying objects that are billions of light years away, making their faint glimmers visible. With advanced mirrors, lenses, and adaptive optics that compensate for atmospheric disturbances, these telescopes can achieve remarkable resolution, revealing internal structures within galaxies that would otherwise appear blurry. The universe doesn't communicate solely in visible light. Other signals, radio waves, infrared, ultraviolet, X-rays, and gamma rays offer unique insights into cosmic phenomena. Radio telescopes, with large dish antennas, detect faint, low-energy signals emitted by pulsars, quasars, and cold interstellar gas clouds. Infrared detectors unveil objects hidden in cosmic dust, allowing us to peer into star-forming regions and the centers of distant galaxies obscured in visible light. X-ray and gamma-ray detectors open a window into the most energetic events: supernova explosions, black hole accretion processes, and high-energy jets from active galactic nuclei. Detectors are the sensitive instruments integrated into these telescopes, converting incoming light into electronic signals that can be analyzed and transformed into images, spectra, or datasets. They are finely tuned to detect even the faintest radiation traveling billions of years across space. Advances in detector technology, like charge-coupled devices, CCDs, for visible light and superconducting sensors for gamma rays, have significantly increased our ability to detect and resolve cosmic signals. These innovations enable astronomers to study celestial objects with extraordinary detail and precision, expanding what we thought was observable. The development of space-based telescopes has revolutionized our understanding by positioning detectors above Earth's atmosphere, which blocks or distorts much incoming light. Instruments aboard satellites such as the Hubble Space Telescope or Chandra X-ray Observatory observe signals impossible to detect from the ground, revealing phenomena related to star formation, galaxy evolution, and the nature of dark matter and dark energy. Thanks to these remarkable observational tools, the universe reveals its secrets in rich detail, many invisible without the dedicated work of telescopes and detectors. They transform distant, faint signals into detailed images and spectra, making the universe's grand narrative accessible to our curiosity and intelligence. Without them, understanding the true scale, history, and complexity of the cosmos would be nearly impossible. Through these technological marvels, we extend our senses across space and time, uncovering stories written in starlight that span billions of years, and revealing how extraordinary and vast our universe truly is. Imagine a future where our gaze extends much further into space, revealing secrets now beyond our reach. New technologies, still in development, promise to expand our cosmic view, peeling back the veils of distance and time that confound us today. One frontier is advanced telescopes capable of observing across the electromagnetic spectrum with unprecedented sensitivity. Currently, we rely on optical telescopes, but the universe is rich in signals, radio waves, infrared, ultraviolet, X-rays, and gamma rays that each reveal unique cosmic phenomena. Improvements in detector technology could make these instruments vastly more sensitive, allowing us to detect faint signals from the earliest stars and galaxies that formed when the universe was just beginning. Future radio telescopes like the Square Kilometre Array, with vast collecting areas, could map large-scale structures with extraordinary detail, uncovering galaxies that appeared hundreds of millions of years after the Big Bang. Complementing this, space-based observatories that detect wavelengths blocked by Earth's atmosphere are expected to advance significantly. Infrared telescopes in space, perhaps free from the limitations of current cryogenics, might peer through cosmic dust clouds with unprecedented clarity. These tools would allow us to study star, planet, and galaxy formation from their earlier stages, seeing so far back that we observed the universe before our solar system existed. Beyond electromagnetic radiation, scientists are exploring gravitational wave observatories like the Laser Interferometer Space Antenna, LISA, which could detect ripples in spacetime caused by massive events, black hole or neutron star collisions, or signals from the universe's birth. Gravitational waves provide a new way to observe the cosmos, unaffected by dust or distance that impede light-based observations. Neutrino detectors are also key. These large underground tanks filled with ultra-pure water or ice can detect elusive neutrinos emitted during energetic astrophysical events. Future, more sensitive neutrino observatories spread across the globe or in space could help trace violent cosmic phenomena from greater distances and earlier times, offering insights into the universe's most energetic processes. Looking further ahead, scientists are contemplating probes travelling at a significant fraction of the speed of light, powered by advancements in propulsion technology. These probes could visit regions of space currently unreachable, providing direct exploration rather than remote observation. Though speculative, such missions might carry instruments capable of viewing the earliest galaxies, offering data that could revolutionize understanding of our cosmic origins. Additionally, quantum communication and computing could transform data transmission from distant observatories, enabling near-instant communication with instruments across the universe. These technologies would allow real-time analysis of phenomena occurring billions of light-years away, bringing the universe closer to us. As our technological toolkit grows, so does our cosmic horizon. Each breakthrough opens a new window into the universe's deepest past and farthest regions, deepening our understanding of our place in this vast cosmos. The universe's vastness is infinite, and each advancement brings us closer to comprehending its grandeur, pushing beyond the limits of light years into the realm of the impossible. Imagine gazing up at the night sky, marveling at the shimmering stars and distant galaxies. It's easy to forget that our view of the cosmos isn't a perfect window. It's haunted by whispers and shadows that shape what we can see and interpret. Cosmic noise and dust are like mischievous artists working behind the scenes, altering the images and data that reach our telescopes. Their influence is subtle but profound, challenging our understanding of the universe's true scale and nature. Cosmic noise is a blanket of faint, unpredictable signals permeating space. It's akin to static on an old radio, created by sources such as remnants of ancient supernovae, the hum of countless distant galaxies, or energetic particles travelling near the speed of light. Although these signals are incredibly faint, they can muddle the clarity of observations. When scientists observe deep space, especially in radio and microwave wavelengths, cosmic noise acts as background chatter, making it difficult to isolate signals from specific objects. It's like trying to hear a whisper in a crowded room. The noise masks details, prompting astronomers to develop sophisticated instruments and data processing techniques to filter static. This challenge limits the precision with which we can measure properties of distant galaxies and phenomena. leaving some parts of the universe just beyond detailed understanding. Dust clouds are physical obstructions, vast regions of tiny icy and carbon-rich particles floating between stars and galaxies. These minuscule grains serve both as obstacles and storytellers. When light from a distant galaxy passes through a dust cloud, it experiences extinction, where the dust absorbs and scatters the light. This process can significantly dim the galaxy's brightness or alter its apparent colours, making it look redder, a phenomenon called reddening. It's like viewing through a foggy window that blurs and tints the scene, hiding some features entirely. Astronomers need to account for dust effects to accurately determine distances, ages, and compositions of galaxies. If overlooked, dust presence can cause us to underestimate how far away objects are or misinterpret their true nature. Sometimes dust doesn't just obscure but acts as a cosmic canvas for new phenomena. When energetic radiation from stars or black holes interacts with dust clouds, it heats the particles, causing them to glow in infrared light. This infrared emission reveals hidden regions of star formation or unseen objects, providing clues about processes otherwise concealed. Dust isn't solely a barrier, it's also a guide, highlighting connections and phenomena that would remain hidden without it. Both cosmic noise and dust influence our cosmic perspective, emphasizing that understanding the universe requires interpreting signals shaped by the universe's own music and smoke. They challenge astronomers to peel back layers of interference, distinguish true signals from static, and see through cosmic fog, inching closer to cosmic secrets. In response, we've refined our tools, developed clever techniques, and gained appreciation for the universe's complex tapestry, a vast, enigmatic, and dynamic space moulded by grand and subtle phenomena. As we peer deeper into the cosmos, we confront a humbling truth. There are boundaries to human knowledge. Light years stretch before us, vast distances that dwarf our understanding, and with each discovery, new questions emerge. Questions that challenge perception and cognition. The universe's infinite complexity whispers that some truths remain beyond our reach, boundaries even light cannot cross within a human lifetime or across generations. The notion of limits inspires philosophical reflection. Is our understanding of reality merely a shadow cast by limited senses and cognition? Are there aspects of the universe so vast or elusive that no technology or reasoning can uncover them? These questions probe knowledge's scope, certainty, and transparency. Some argue perception is inherently limited. Our senses evolve for survival in a tiny universe corner, not to understand its full scope. For example, our eyes perceive only a narrow electromagnetic spectrum, yet the universe resonates beyond our hearing or detection. This suggests understanding is conditioned and partial. Scientific instruments extend our senses, revealing layers of cosmic reality, but even these tools have thresholds. Philosophically, tension exists between empiricism and rationalism, between observation and inference. Light conveys truths about distant phenomena, yet it also introduces uncertainty. The farther it travels, the more it is affected by redshift, encoding the universe's history and possibly its future. Do these signals reveal the whole story, or are they fragments filtered through cosmic dust and interpretation limits? Infinity also plays a role. The universe might be infinitely large and forever receding, making complete knowledge impossible. Even with advanced observation, some regions remain forever hidden, behind event horizons or beyond the observable universe. This raises existential questions. If truths lie beyond our horizon, do they matter? Or are they simply unknowable parts of an infinite cosmos, urging humility? Within these limits lies a paradox. Human curiosity is boundless. Our desire to know drives us to develop better tools and theories. Each discovery reveals astonishing truths, but also uncovers new mysteries. The universe appears as an intricate mosaic, with each answer prompting further questions. This dynamic between knowledge and the unknown fuels philosophical thought. It challenges us to consider whether ultimate truths, cosmic or metaphysical, are forever beyond grasp, or if knowledge is an infinite pursuit. Perhaps the real beauty of cosmic discovery is that it illuminates not only the universe, but also human wonder and humility. Some mysteries, it seems, are woven into the universe's eternal tapestry and may never be fully unravelled. Our continual quest for understanding is both humbling and inspiring. Limitations remind us of our finite place amidst the infinite, yet they also fuel our drive to explore. The universe's grandeur invites awe, an infinite frontier that both beckons and eludes. In pondering these boundaries, we find ourselves confronted with the profound realization that some truths may remain forever beyond reach, a humbling testament to the infinite mystery at the heart of existence. Even so, human curiosity persists, ever pushing forward, seeking meaning in the vast unknown cosmos. Einstein's theory of relativity fundamentally transformed our understanding of space and time, challenging and replacing the Newtonian conception of an absolute universe. Before Einstein, space was thought to be a static, unchanging stage where events occurred, and time was regarded as ticking uniformly for all observers, independent of their motion. However, Einstein's insights revealed that space and time are inherently linked within a four-dimensional fabric called spacetime, which is dynamic, flexible, and influenced by mass and energy. Imagine observing a train moving at high speed through a station. According to Newton, both the train and a stationary observer would agree on measurements of length, time intervals, and simultaneity. Einstein's special relativity, however, demonstrates that these measurements depend on the frame of reference. As objects approach the speed of light, lengths along the direction of motion contract, a phenomenon known as length contraction, and time dilates, meaning clocks moving at relativistic speeds tick more slowly relative to stationary observers. These effects, negligible at everyday velocities, become significant as one approaches the speed limit set by light. Delving deeper, Einstein showed that gravity is not a mysterious force acting instantaneously at a distance, but instead results from the warping or curvature of spacetime caused by mass and energy. Massive objects such as stars, planets, and black holes create dents in this fabric, altering the paths that objects and light rays follow. These curved paths are what we perceive as gravity. For example, during a solar eclipse, light from distant stars was observed to bend around the sun, confirming Einstein's prediction that gravity influences light itself, a phenomenon known as gravitational lensing. This was a key experimental validation of his general theory of relativity. Einstein's insights also impact our understanding of simultaneity. Two events that occur simultaneously in one frame of reference may not be so in another, moving at a different velocity. This reconceptualization means there is no absolute universal clock ticking the same everywhere. Time becomes relative, dependent on the observer's motion. Additionally, the universe appears interconnected and dynamic. Space itself can stretch, warp, or even tear under extreme conditions, such as near black holes, profoundly affecting the structure and fate of the cosmos. The practical consequences of relativity are widespread. GPS satellites orbiting Earth must account for both special relativistic effects, due to their relative motion, and general relativistic effects, due to weaker gravity at their altitude, to provide accurate positioning data. Without these adjustments, navigation systems would quickly become inaccurate. Moreover, Einstein's theory lies at the heart of modern astrophysics, informing our understanding of phenomena such as black holes, gravitational waves, and the expansion of the universe. It also means that we see distant parts of the cosmos as they were in the past, because the finite speed of light delays information reaching us. Thus, telescopes are time machines peering into cosmic history. Ultimately, Einstein's relativity reveals that space and time are not separate, absolute entities, but interconnected, malleable, and profoundly influenced by matter and energy. This worldview challenges our intuition and expands our sense of the universe's complexity, beauty, and wonder, making space and time more alien and captivating than ever before. Imagine the universe not as a simple backdrop where things happen, but as a woven fabric, a sprawling dynamic tapestry called spacetime. It's a concept that unifies space and time into a single four-dimensional fabric, one woven so tightly that they can't be separated. When we think of the universe, we often picture planets, stars, galaxies, and the vast emptiness between them. But these objects aren't just floating in empty space, they interact with the very fabric of spacetime itself. Think of spacetime as a stretchy sheet of rubber. When you place a heavy object like a bowling ball onto the sheet, it creates a dip, an indentation that distorts the surface. Now imagine rolling a smaller ball, say a marble, near that indentation. It will spiral inward, not because there's some invisible force pulling it directly, but because it's simply following the curved contours of the fabric. In a similar way, massive objects like stars and black holes warp spacetime around them, and this curvature guides the motion of smaller objects and even light. This warping of spacetime isn't just a metaphor, it's the heart of Einstein's general theory of relativity. He proposed that what we perceive as gravity isn't a force pulling objects together, but the result of objects following curved paths, geodesics, through the warped fabric. The greater the mass or energy concentrated in one place, the more pronounced the curvature. It's like dropping a large boulder onto that rubber sheet. The deeper the dip, the stronger the influence on anything rolled nearby. Energy, in all its forms, whether it's heat, radiation, or even the energy of a moving object, also contributes to this curvature. Einstein's famous equation, E_mc², tells us that energy and mass are interchangeable. Mass is just a form of concentrated energy. When energy is present, it also curves the space-time fabric. This means that not only massive objects like stars and planets warp space, but energetic phenomena like intense radiation or electromagnetic waves do too. This warping has profound effects throughout the universe. It influences the orbits of planets, the paths of comets, and the bending of light as it passes near massive objects, a phenomenon known as gravitational lensing. When light travels through curved spacetime, its straight-line path appears bent to an observer, allowing astronomers to detect and measure the warping around massive galaxies and black holes. This isn't just theoretical, it's a directly observable consequence, like seeing the distorted image of an object bent around a glass of water. In fact, the very expansion of the universe itself stretches spacetime, causing galaxies to drift apart over billions of years. The fabric of spacetime is dynamic, constantly responding to the presence of mass and energy, expanding, contracting, and warping as the cosmos evolves. So, understanding spacetime isn't just about grasping the structure of the universe, it's about realizing that everything, matter, energy, light, and even the very fabric of reality, is interconnected through this intricate, ever-changing cosmic web. Imagine the fabric of spacetime as an endless four-dimensional sheet stretching across the universe. When massive objects like black holes or neutron stars dance around each other or collide in spectacular mergers, they don't just ripple, they send out oscillations that ripple through this fabric, much like waves spreading across a pond surface when a stone is thrown in. These ripples are what we call gravitational waves. Gravitational waves are incredibly elusive. Unlike light or sound, they don't bounce off objects in the traditional sense or travel through a medium like air or water. Instead, they stretch and squeeze spacetime itself, producing tiny distortions that travellers on Earth can in principle detect. Their discovery in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO, opened a new window onto the universe, revealing an entirely different way of observing cosmic phenomena. What makes gravitational waves so remarkable is how they demonstrate that spacetime isn't a static backdrop but a dynamic, malleable entity. When massive objects accelerate, say two black holes spiraling closer and closer, they create ripples that travel outward at the speed of light. These ripples carry information about the most violent events in the cosmos, encoding details about how the objects moved and interacted. As these gravitational waves pass through us, they cause space to stretch in one direction and contract in another within tiny fractions, much less than a single atom's width. Detecting these minuscule signals requires exquisitely sensitive instruments, like LIGO and Virgo detectors, which use laser interferometry to measure changes in distance on the order of 1/10,000th the diameter of a proton. It's as if they're listening for faint whispers of cosmic cataclysms across the vastness of space. Observing gravitational waves confirms that spacetime responds dynamically to the presence and movement of mass and energy. When massive objects accelerate, they cause spacetime to oscillate, revealing its fluid-like nature. This is a profound realization. Space and time aren't rigid containers, but are elastic and responsive. They can ripple, warp, and ripple again, depending on the cosmic choreography unfolding around us. Furthermore, gravitational waves allow us to probe regions of the universe that are otherwise hidden from view. Light can be blocked or absorbed, but gravitational waves pass through matter almost unimpeded. This means we can detect events that are shrouded in thick gas clouds or dust, like the core of a black hole's merger, giving us renewed insight into their processes. Analyzing these ripples also tests Einstein's theory of general relativity in its most extreme environments. The waveforms we observe match the predictions of the theory with astonishing precision, reinforcing Einstein's view that gravity is not a force acting at a distance, but a curvature of space-time itself. Even more intriguingly, gravitational waves might someday unveil phenomena we have yet to imagine, such as signals from the universe's earliest moments so distant and distant from our own that their echoes are trapped in the fundamental structure of space-time, whispering stories from the dawn of everything. In all these ways, the detection and study of gravitational waves turn out to be a key to understanding the universe's dynamic, ever-changing fabric, showing us that space-time itself is not a static stage but a lively, breathing entity woven with the threads of cosmic motion. Relativity, especially Einstein's theories, special and general, revolutionizes our understanding of the universe. When considering cosmic objects and their extreme speeds, classical notions of absolute time and space bend, revealing phenomena like time dilation. Special relativity, introduced in 1905, states that as an object approaches the speed of light, time for that object runs slower compared to someone at rest. Imagine a spaceship travelling near light speed with a clock on board. From Earth, the clock appears to run slow, but on board, the crew perceives their time as normal, and it's the external universe that seems to tick faster. This is a fundamental property of space-time. Relativistic effects are vital when dealing with particles or light travelling near light speed, such as cosmic rays or neutrinos. For example, muons created in Earth's upper atmosphere decay quickly, but because they travel so fast, their internal clocks run slow, allowing them to reach the surface, a process explained by time dilation. Celestial phenomena also show relativity's influence. Distant quasars or pulsars, extremely luminous objects emitting jets at speeds close to light, exhibit signals affected by relativistic effects. Their emitted light is redshifted, partly due to universe expansion, but also because of their high velocities causing time dilation. Quasars' brightness and variability suggest energetic processes occurring near light speed, highlighting relativity's role. The fabric of space-time isn't fixed but dynamic, intertwined with motion and gravity. General relativity further extends these ideas, describing how gravity influences time. Massive objects like black holes, neutron stars, and galaxies curve space-time. Clocks near these dense masses tick more slowly than those farther away. For instance, a spaceship near a galaxy's center would observe its clock running slower due to gravitational time dilation. Experiments on Earth, such as comparing atomic clocks at different altitudes, confirm this effect. Near a black hole's event horizon, gravitational time dilation intensifies. From an external perspective, time appears to almost freeze at the boundary. In the universe, where galaxies collide, or where light from ancient stars takes eons to reach us, relativity provides crucial insights. It explains why clocks on near-light speed spacecraft measure time differently, why cosmic events seem slowed or frozen, and supports understanding the universe's expansion and redshifted light from distant galaxies billions of light-years away. These effects challenge the idea of a universal, absolute clock ticking uniformly everywhere. Instead, they depict a universe with fluid time, warped, stretched, and compressed by motion and gravity. Our view of the cosmos becomes more extraordinary, revealing a dynamic space-time dance. Each step is influenced by energies and velocities, and the experience of time depends on where you are and how fast you're moving. Relativity's insights illuminate the interconnectedness of time, gravity, and motion, shaping a universe more wondrous and complex than previously imagined. The universe can be envisioned as a vast, malleable fabric, an intricate quilt of space-time, rather than a flat, unchanging stage. This fabric, space-time itself, is what Einstein described in his theory of general relativity. Instead of gravity being a simple force pulling objects together, Einstein explained it as the curvature of space-time caused by mass and energy. Massive objects like stars, black holes, and galaxies warp this fabric, creating curves and dents that influence everything around them. How does this curvature shape the path of light? Unlike objects with mass, light has no rest mass and travels along what are called null geodesics, paths representing the straightest possible lines in a curved spacetime. These paths aren't straight in the traditional sense. They're curved because of the fabric's warping. To visualize this, imagine a stretched trampoline with a heavy ball placed in the center. The The fabric dips around the ball, creating a curved landscape. When a marble is rolled across this surface, its path bends around the dip, even though it moves straight in its own frame. Similarly, light moves along curved paths in space-time, which can cause it to change direction, a phenomenon known as gravitational lensing. Gravitational lensing vividly demonstrates how space-time curvature affects light. When light from a distant galaxy passes near a massive object, such as a galaxy cluster, the curvature causes the light's path to bend. The more massive the object, the more pronounced the bending. This can produce multiple images of the same distant object or Einstein rings, bright rings of light. Essentially, the universe's most massive structures act as cosmic magnifying glasses, distorting and bending the light reaching us across millions or billions of light years. The influence of space-time curvature on light extends further. When the universe expands, space stretches, elongating the paths of light beams travelling through it. This stretching shifts the light's wavelength toward the red spectrum, a process called redshift. This isn't just a colour change, it's a direct consequence of photons climbing out of the expanding space-time well, losing energy as space around them expands. The farther the source, the longer the light has travelled, and the more it's been stretched by cosmic expansion. This enables astronomers to look back in time, observing galaxies as they were billions of years ago. The curvature of space-time isn't static. It evolves with the universe's changing density, dark energy, and matter distribution. These shifts influence our observations of distant galaxies, quasars, and the cosmic microwave background, the faint glow left over from the Big Bang. The universe's overall shape, whether open, closed, or flat, determines how light paths converge or diverge, affecting what we see when we peer into space's depths. In essence, the curvature of space-time guides light across the cosmos. It bends, shifts, and warps photons travelling through the universe, shaping the cosmic landscape we observe. Every distant star or galaxy's light whispers about space-time's shape, a delicate dance between light and gravity. This dance reveals a universe far more dynamic and interconnected than it appears. Understanding it deepens our appreciation for its complexity. The more we grasp this interaction, the more incredible the universe becomes, stretching our minds to comprehend the truths woven into its very fabric. Word count 480. Black holes are regions in space where gravity becomes so intense that nothing, not even light, can escape. They form when massive stars exhaust their fuel, collapsing under their own weight during a supernova explosion. The remnant core becomes an extremely dense point called a singularity, surrounded by the event horizon, the boundary beyond which nothing returns. Because black holes are invisible, they trap all light within the event horizon. They are detected indirectly by their effects on nearby matter and light. When a black hole encounters gas, dust, or stars, its enormous gravity pulls these objects inward. As matter spirals into an accretion disk, it heats up to emit intense X-rays and radiation detected by telescopes, signaling the black hole's presence. Black holes significantly influence the light passing near them. Their gravity warps space and time, causing the path of light to bend, a phenomenon called gravitational lensing. For example, light passing close to a black hole can be distorted or magnified, creating multiple images or rings around the black hole, known as Einstein rings. Sometimes distant galaxies viewed through a black hole's gravitational field appear stretched or duplicated. The gravity near a black hole also causes gravitational redshift. Light escaping from a strong gravitational field loses energy and shifts toward the red end of the spectrum. As light climbs out of the black hole's gravity well, it becomes increasingly redshifted. Observers can analyze this redshift to determine the strength of the gravity near the event horizon. Black holes can influence the timing and appearance of light signals. Events near a black hole, such as a star's material falling in or a flare, may produce light that reaches us delayed or distorted. The intense gravity can cause light to take multiple paths, creating echoes or time delays. These effects provide insights into the shape and curvature of space in extreme environments. Stephen Hawking's theory of Hawking radiation suggests black holes aren't entirely black. They can emit particles over long timescales, slowly losing mass and eventually evaporating. This emission is nearly impossible to detect with current technology, but challenges existing physics, blending quantum mechanics with gravity, and opening questions about the ultimate fate of black holes. Black holes are more than cosmic vacuum cleaners. They serve as natural laboratories for studying gravity, quantum mechanics, and light. Their ability to bend and influence light reveals phenomena occurring under the universe's most extreme conditions. The intense warping of light and space-time near black holes allows scientists to probe fundamental physics, pushing the boundaries of our understanding. Advancements in observational technology continue to reveal more about these mysterious objects. While their darkness keeps them hidden, the effects they produce, lensing, redshift, time delays, provide key clues. Studying black holes enhances our knowledge of the universe's evolution, the nature of space and time, and the fundamental laws of physics. In essence, black holes embody the universe's extremes. They distort light and space in ways that challenge and expand scientific theories. As research progresses, black holes remain pivotal in unlocking the universe's deepest secrets, reminding us that some of the most profound mysteries lie in the darkness, waiting to be understood. Imagine a cosmic shortcut, a tunnel that cuts straight through the fabric of space-time, connecting two distant points in the universe. Wormholes, sometimes called Einstein-Rosen bridges, have long captured the imagination of scientists and science fiction writers alike. But could they truly serve as cosmic portals, enabling us to traverse the vast distances of space in the blink of an eye? The idea is tantalizing. If light takes years, centuries, or even millennia to reach the most distant galaxies, then perhaps wormholes could offer a shortcut, allowing us to sidestep the light-year barrier and explore the universe more swiftly. The concept starts with the fabric of space-time itself, the four-dimensional structure that combines the three dimensions of space with time. General relativity, Einstein's masterpiece, predicts that this fabric can become warped and curved under the influence of mass and energy. Wormholes are theorized as tunnels with two ends connected through a higher dimensional space, akin to a worm crawling through an apple's skin and connecting 2 points on the surface. If such structures exist, they could, in theory, provide a bridge between distant regions of space-time, shortening what would otherwise be an unimaginably long journey. However, jumping through a wormhole isn't straightforward. The mathematics of wormholes suggest they would be inherently unstable, collapsing almost instantly under their own gravity, unless some form of exotic matter with negative energy density is present. Exotic matter is a mysterious and hypothetical substance that defies many of the known laws of physics, and as of today, no experimental evidence confirms its existence. Without it, a wormhole would pinch itself shut before anyone could pass through. Even if stable wormholes could be created or stabilized, there's another hurdle: causality. Traveling faster than light could lead to paradoxes. Think of the famous grandfather paradox, where an effect could precede its cause. Such situations threaten the very logical consistency of our universe's laws. To avoid these paradoxes, some physicists propose that the universe might impose strict rules on faster-than-light travel, possibly preventing wormholes from being used as shortcuts for actual travel. Yet, the mathematics of quantum gravity, an elusive theory aiming to unify general relativity with quantum mechanics, may hold answers, potentially revealing new insights into whether wormholes could serve as genuine bridges across cosmic distances. In the realm of science fiction, wormholes are often depicted as readily accessible portals, allowing characters to jump across galaxies in moments. But reality is far more complex. Despite what physics models suggest, we're still far from understanding whether such structures could exist or be harnessed for travel. They remain theoretical constructs, beautifully intriguing and rich with possibility, but still dangling on the edge of scientific plausibility. Still, the very concept pushes us to rethink what's possible, challenging our understanding of distance, causality, and the very fabric of the universe itself. Until we unlock deeper secrets of the cosmos, wormholes remain fascinating hypotheses, possible cosmic bridges, or perhaps just a well-crafted fantasy inspired by the intricate elegance of Einstein's universe. But as our understanding advances, who knows? Maybe someday, light years will no longer be barriers, but merely mileposts on an extraordinary journey through the infinite universe. Imagine approaching a black hole, the most enigmatic and powerful objects in the universe. As you draw nearer, something strange begins to happen. There exists a boundary known as the event horizon. It's not just a border, it's a point of no return. Once anything crosses this invisible line, whether it's a beam of light, a spaceship, or a curious observer, there's no coming back. The event horizon can be thought of as the ultimate cosmic cliff. To understand it better, picture a river flowing towards a waterfall. Upstream, everything is calm and manageable. Downstream, the water rushes over the edge, impossible to stop. The event horizon is like that edge for light and matter, plunging into a black hole, the point beyond which escape becomes impossible. The gravity near a black hole is so intense that the escape velocity, the speed needed to break free, exceeds the speed of light. Because nothing can travel faster than light, even light itself cannot escape once it crosses this boundary. What does this mean for light? It's both haunting and fascinating. Imagine shining a flashlight towards a black hole. Some of the light will be pulled in, spiraling downward. Once it crosses the event horizon, the light is lost forever to the outside universe. From our perspective, the light begins to stretch out and fade, getting redder and dimmer as it approaches the horizon. To an observer far away, the light from objects falling into the black hole appears to slow down and freeze as it nears the event horizon, never quite seeming to cross it. This phenomenon is tied to the warping of spacetime caused by the black hole's gravity. For matter, stars, gas clouds, even entire galaxies, the story is similar but even more intense. Anything that ventures past the event horizon is destined to be crushed into the singularity, a point of infinite density at the core of the black hole where our current understanding of physics breaks down. In this realm, space and time are twisted beyond recognition, and traditional concepts of cause and effect become meaningless. The significance of the event horizon extends far beyond black holes themselves. It helps us grasp the ultimate limits of the universe and how gravity can reshape reality. For example, the event horizon marks a boundary beyond which information cannot reach us. This leads to profound questions about what happens to the information contained within objects that fall in, conundrums that challenge our understanding of physics and have sparked debates for decades. The event horizon also acts as a cosmic signpost, reminding us of how mysterious the universe truly is. It signifies a point where the classical laws of physics seem to give way to the unknown, where space and time intertwine in ways that defy intuition. It stands as a symbol of the universe's most extreme and mind-boggling phenomena, embodying the idea that our universe is a place full of boundaries, both visible and invisible, that shape the very fabric of existence. So, the event horizon isn't just a boundary, it's a gateway to understanding the limits of our universe, the nature of gravity, and what happens when the fabric of space-time bends to the breaking point. It's a reminder of how much there is that we still don't fully comprehend about the universe's deepest mysteries. Black holes might seem like cosmic vacuum cleaners, devouring everything nearby with relentless gravity, but their true power lies in the secrets they reveal about the vast universe. When astronomers observe black holes, especially the ones actively swallowing matter or merging with others, they're not just studying gravitational monsters, they're peering into the fabric of space itself, unraveling clues about cosmic distances that stretch across millions, even billions of light years. One of the key ways black hole observations help us understand the universe's grand scale is through the light emitted or affected by matter near these mysterious entities. As matter spirals into a black hole, it heats up, releasing high-energy radiation like X-rays and gamma rays. By analysing these signals, scientists can glean information about the black hole's properties, but also about how far away it is. This is because the intensity and energy of the radiation diminish with distance, a fundamental principle rooted in the inverse square law. So, if we know what a black hole should look like at a certain luminosity, we can estimate its distance based on how bright it appears to us. But black holes don't just provide direct measurements of distance, they also serve as cosmic markers that weave together the fabric of cosmic history. For example, when a black hole merges with a neutron star or another black hole, the gravitational waves rippling through space-time can now be detected by observatories like LIGO and Virgo. These gravitational waves carry with them a direct imprint of the distance to the event, essentially acting as a cosmic yardstick. By measuring the strength and shape of these waves, scientists can determine how far away the merger took place. These measurements are invaluable because they aren't dependent on traditional cosmic distance ladders, which rely on a chain of assumptions and calibrations. Furthermore, some black holes live in the centers of distant galaxies, acting as luminous beacons that help trace the universe's expansion. Supermassive black holes, which are millions or even billions of times the mass of our Sun, can emit intense radiation that, when observed carefully, helps constrain the distance to their host galaxies. When combined with redshift measurements, how much the light from that galaxy has been stretched by the universe's expansion. These observations help refine our estimates of cosmic scale and rate of expansion. Black hole observations also shed light on the universe's infancy. By studying the light and gravitational waves from distant black holes, astronomers can look back billions of years into cosmic time. These ancient signals serve as a window into the early universe, offering insight into how structures like galaxies and black holes formed. Each of these signals is like a message from the distant past, with its journey across cosmic distances telling us just how far these signals have travelled. In this way, black holes are more than destructive phenomena, they are cosmic signposts. Each observation, each flicker of radiation or ripple through space-time helps us chart the universe's vast, mysterious landscape. They're like cosmic lighthouses, illuminating the path to understanding how far we've come and how immense this universe truly is. A wormhole is a hypothetical tunnel through space-time that could connect distant regions of the universe instantly. Originating from Einstein's general relativity, which describes how mass and energy warp space-time creating gravity, solutions suggest such tunnels might exist. These are often depicted as shortcuts, but they require conditions far beyond current understanding. The existence of solutions does not guarantee wormholes are real or stable. For a wormhole to be useful, it must be traversable without collapsing or crushing a traveller. Most solutions imply they would be highly unstable, collapsing quickly unless influenced by some form of extraordinary matter. This leads to the idea of exotic matter, which would stabilise a wormhole. Such matter would need to have negative energy density, a concept that contradicts known physics, since all matter is positive energy. Quantum phenomena, like the Casimir effect, hint at negative energy on tiny scales, but scaling this up to stabilise a large, traversable wormhole remains beyond current technology, and might even be impossible. If stable, large wormholes could revolutionise space travel, allowing humans to reach distant stars within a lifetime. Instead of centuries, journeys could be instantaneous, making exploration of distant planets and even intergalactic colonisation feasible. They could enable sharing knowledge across light years and open up entirely new possibilities for humanity. Beyond practical travel, wormholes raise profound questions about causality, the relationship between cause and effect. Travelling back in time through a wormhole could create paradoxes, such as the grandfather paradox, where a traveller might prevent their own existence. Physicists debate whether the laws of nature prevent such paradoxes or if concealed principles preserve causality. Wormholes might also challenge our understanding of the universe's structure, potentially connecting different parts of our universe or even different universes within a multiverse. Such connections could allow faster-than-light communication, but this remains speculative and faces significant theoretical obstacles. If discovered or engineered, wormholes could profoundly alter science and technology. They could enable instant travel across cosmic distances, revolutionizing exploration and colonization. They might also allow for new forms of communication, or even influence our understanding of time and reality itself. Currently, wormholes are purely theoretical constructs. They exist at the edge of what we know and what we do not. They symbolize the mysterious possibilities of the cosmos, stretching our notions of space and time. They embody the hope that future physics might unlock these tantalizing secrets. Wormholes emphasize the tension between current understanding and the unknown. They challenge conventional ideas about the fabric of the universe, pushing the boundaries of science and imagination. If ever discovered or created, they could transform travel, communication, and our grasp of the universe's fundamental nature. For now, wormholes remain speculative yet inspiring. They serve as a reminder of how much we have left to learn about the cosmos. The search for understanding continues, opening doors to new physics and possibly transforming the impossible into the possible someday in the future. Their study fuels curiosity and exploration, embodying humanity's innate desire to unlock the universe's deepest secrets. The expansion of the universe is a mind-boggling phenomenon that fundamentally changes the way we perceive distant galaxies. Imagine the universe as a giant, stretching fabric, every galaxy embedded within it, carried along like leaves on a flowing river. As this cosmic fabric expands, it stretches the light travelling through it, and this stretching has profound effects on what we observe and how we interpret the universe's history. When light journeys from a distant galaxy towards us, it's not just moving through empty space, It's moving through a universe that is continually getting bigger. Because of this, the wavelengths of that light don't stay the same. They are stretched out, or redshifted. This shift to longer wavelengths is why we call it redshift. The more distant the galaxy, the faster the universe is expanding between its emission of light and our detection of it. That means the light from galaxies billions of light years away arrives, stretched into the red part of the spectrum, indicating that the universe was much smaller and denser when that light first began its journey. This redshift isn't just a pretty effect, it's a cosmic signpost that reveals the universe's expansion. By measuring how much the light from a galaxy is redshifted, astronomers can determine how much the universe has stretched since the light left the galaxy. This, in turn, allows us to estimate how far away the galaxy is, giving us a window into the universe's past. Essentially, every photon that reaches us from distant galaxies is a messenger carrying historical information, frozen in the light's shifted wavelengths, telling us what the universe looked like billions of years ago. But the expansion influences more than just the light's wavelength. It also affects how we understand the universe's age and size. When we look at galaxies billions of light years away, we are looking back in time, seeing these galaxies as they were when the universe was much younger. The faster the universe expands, the more distant and ancient these galaxies seem. The expansion acts like a cosmic time machine, allowing us to piece together the story of galaxy formation, evolution, and the universe itself. Interestingly, recent observations suggest that the expansion rate isn't constant. Instead, it's accelerating, driven perhaps by mysterious dark energy. This acceleration stretches the fabric of space at an increasing pace, affecting how galaxy light is redshifted over cosmic time. Understanding this acceleration is at the forefront of modern cosmology, as it holds clues to what's powering the universe's growth. So the universe's expansion doesn't just spread galaxies apart, it profoundly influences the very light that reaches us, offering glimpses into epochs long past. Each photon's journey echoes the universe's dynamic story, an endless dance between space, time, and light that continually reshapes our understanding of the cosmos. Hubble's law is one of the most profound discoveries in astronomy, a revelation that transformed our understanding of the universe's vastness and its dynamic nature. At its core, Hubble's law describes the relationship between the speed at which a galaxy is moving away from us and its distance from Earth. It states that the farther a galaxy is, the faster it appears to be receding. This might seem simple on the surface, but it holds the key to understanding that the universe is expanding everywhere, not just in one direction. Imagine observing a multitude of galaxies scattered across the cosmos. When Edwin Hubble first measured their velocities, how fast they're drifting away, we find something astonishing. The galaxies aren't speeding off randomly, instead they follow a clear pattern. The redshift we observe in their light, caused by the stretching of light waves as they travel through expanding space, corresponds directly to their distance from us. This redshift indicates that the galaxies are moving away, and the greater their distance, the faster they are retreating. Hubble's law is succinctly expressed as a stierchast vuls vul h001 times d, and where wum vul stierchast represents the galaxy's recessional velocity, wu dl is the distance to the galaxy, and gifast Hubble's constant sets the rate of expansion. This constant is like a cosmic speed limit, telling us how quickly the universe is growing in every direction. Although its precise value has been refined over decades, Hubble's law remains a fundamental tool for measuring cosmic distances. This relationship is not just about measuring how fast galaxies are moving away, it changes the entire perspective of the universe. It's as if the universe is a loaf of raisin bread dough that's rising. Every raisin, galaxy, moves away from every other raisin, and the farther apart they are, the faster they're receding. If you imagine placing ourselves at any point in this expanding universe and looking outwards, we would see galaxies rushing away from us with velocities proportional to their distances. No special center exists. The expansion happens everywhere simultaneously. Hubble's law allows astronomers to estimate how far away galaxies are by measuring their redshift, the shift in wavelength of their light, and converting that into a velocity. Once we know the galaxy's speed, we can determine its distance. This method is especially powerful for the most distant galaxies, where other techniques like parallax are no longer feasible. because of the vast scales involved, but the implications go even further. Hubble's law reveals that the universe was once much smaller, denser, and hotter, a cosmic egg waiting to hatch. By calculating how fast galaxies are speeding away, scientists can work backwards to estimate the universe's age, leading to the fascinating realization that our universe has been expanding for around 13.8 billion years. In this way, Hubble's law not only maps the enormous distances separating galaxies, but also narrates the story of the universe's evolution, a story written in the language of light, stretching across light years, and telling us that everything is constantly expanding into the vast unknown. The accelerated expansion of the universe is one of modern cosmology's most astonishing discoveries. It's as if the universe has stepped on the gas pedal, racing outward faster and faster, stretching space itself at an increasing rate. But how does this speeding up impact our future observations? First, consider how accelerated expansion affects light travelling through space. As space expands, it stretches the wavelengths of photons, a process called redshift. The faster the expansion, the more these wavelengths are stretched as light travels toward us. Over cosmic timescales, this causes distant galaxies to appear increasingly redshifted. Their light shifts toward the extreme end of the electromagnetic spectrum, eventually moving outside our current detection range. Practically, objects billions of light years away may eventually become unobservable, because their light becomes too stretched to detect with existing telescopes. This process significantly impacts the cosmic horizon, the furthest distance from which light has had time to reach us since the Big Bang. Due to accelerated expansion, this horizon recedes at an ever-accelerating rate. Objects currently within our observable universe will eventually drift beyond our reach, their light unable to reach us within cosmic time. It's as if the universe is creating an expanding wall, isolating parts of the cosmos from view forever. Over hundreds of billions of years, much of what we now see will be lost, leaving only galaxies gravitationally bound to our local group. Furthermore, accelerated expansion influences the formation and evolution of structures. As space expands swiftly, it counteracts the gravitational attraction that gathers matter into stars, galaxies, and clusters. This means the universe's large-scale structure will become increasingly sparse. Future observers, if any exist, might see a universe that appears incredibly empty, with distant galaxies gone and only a few nearby ones still observable. The expansion effectively isolates galaxies, preventing light from distant sources from ever reaching us. There are also bleak implications regarding the universe's ultimate fate, often called the Big Freeze or heat death. As galaxies disappear beyond the horizon and space continues stretching, the universe will cool and darken. Stars will burn out and no new stars will form. Future astronomers might observe only faint remnants of a once vibrant cosmos. Without the glow of distant galaxies and quasars, the night sky could turn into a silent, empty void, shrinking the observable universe both in size and in the diversity of objects seen. In essence, accelerated expansion acts as a double-edged sword. It allows us to peer back into the universe's past by observing distant objects, but it also limits future observation. As the universe accelerates outward, the observable horizon will shrink, making the universe more isolated and mysterious. The same expansion that uncovers the universe's origins also gradually obscures its future, leading to a universe that's fragmented and less luminous than we can now imagine. When we observe the light coming from distant galaxies, we often find it shifted toward the red end of the spectrum, a phenomenon known as redshift. This subtle change isn't just a quirk of physics, it's a cosmic messenger, whispering secrets about the history and expansion of the universe itself. Redshift occurs because the universe is stretching out, and as space expands, it stretches the light travelling through it, increasing its wavelength and shifting it toward the red end of the spectrum. The more distant the galaxy, the more its light is stretched, which directly ties redshift to how far away and how long ago the light was emitted. This stretching reveals a profound story. The universe was once much more compact and energetic. When we see light from galaxies that are billions of light years away, we are literally looking back in time. We see those galaxies as they were billions of years ago, shortly after the universe's birth. As the light journeyed across the cosmos, the universe expanded, and this expansion has continued ever since. By measuring the degree of redshift, astronomers can determine how fast a galaxy is receding from us, which in turn provides a snapshot of the universe's expansion rate at different points in its history. In essence, redshift acts as a cosmic clock. Consider a galaxy with a redshift so high that its light has travelled for over 10 billion years to reach us. That galaxy's light reveals what the universe looked like long before humans existed, painting a picture of primordial galaxies swirling with chaos, birth, and collision. The degree of redshift tells us whether the universe is accelerating or slowing down in its expansion.